Shao from the Institute of Advanced Study, and the title is Beyond Symmetry, Topological Lines in Two Dimensions. Please.
Thank you. First of all, I would like to thank the organizers for putting together this wonderful conference and giving me this chance to present my work here. Today, I'm going to talk about Beyond Symmetry, Topological Lines in Two Dimensions. This is based on work with Qiming Cheng, Yingxuan Lin, Yifan Wen, and Shi Ying. All right, so let me start with the power of symmetry, which we have heard a lot in this morning. Symmetry has always been a guiding principle in theoretical physics. Global symmetries are powerful in constraining RG flows, correlation functions, and all other physical observables. As we have heard in the talks in this morning, when the global symmetry has the 't Hoof anomaly, it's especially powerful in constraining the IR structure of RG flows. And ward identity of global symmetries are useful to constrain the correlation functions. And also, global symmetries are usually the first thing we check when verifying dualities. More recently, there has been a lot of development on higher form global symmetries. These are global symmetries that can be coupled to higher form gauge fields. And they have also shown to be very powerful in constraining the dynamics of quantum field theory. One invariant characterization of global symmetry is in terms of its charge operator, also known as the topological defect. And that would be one of the main players in today's talk. Topological defect might sound like a very fancy word, but it actually isn't. It's something we are very familiar with. In the case of continuous global symmetry, it's nothing but the Noether charge. To be more precise, it's the exponentiation of the Noether charge. The Noether charge is supported on a codimension 1 manifold in our spacetime, which is usually taken to be a constant time slice. It is useful to think of it as a topological defect. It is topological because when we deform the codimension 1 manifold a little bit without passing through any local operator, that wouldn't change the correlation function. This follows from the conservation of the Noether current. More generally, for any zero-form global symmetry, continuous or discrete, there's an associated codimension 1 topological defect, which I will denote by L sub G, where the subscript G labels the group element of the global symmetry. The charge operator, or equivalently the codimension 1 topological defects, acts on local operator by encircling it. Once we encircle the local operator by this codimension 1 topological defect, we can shrink the defect to be smaller and smaller and smaller. In that process, all the correlation function will remain invariant because it's topological. So at the end of the day, we produce another local operator on the right-hand side, which is related to the previous one by a symmetry transformation. So to sum up so far, given any zero-form global symmetry, there's an associated codimension 1 topological defect, namely its charge operator. The main question we would like to address today is whether the converse arrow is true. Namely, is every codimension 1 topological defect in a quantum field theory associated to a zero-form global symmetry? The answer is no. There are codimension 1 topological defects that are not the charge operators of any zero-form global symmetry. So the slogan of the talk today will be the power of non-symmetry instead of the power of symmetry, as we have heard a lot this morning. I will loosely refer to this defect as the non-symmetry topological defect. The technically more precise term will be non-invertible defect, for reasons that we will see momentarily. But in this talk, I would like to contrast the symmetry defect with this non-symmetry defects more clearly. So I will use this more sloppy terminology. As it turns out, these non-symmetry topological defects are equally powerful in constraining the dynamics of quantum field theory. So far, it might sound like this non-symmetry topological defect is something totally exotic and exists only in special CFTs. But we don't actually have to look far for such defects. They are ubiquitous in two-dimensional conformal field theory. For example, there's already one such non-symmetry topological defect in the two-dimensional Ising CFT. So here's a little roadmap. on how this talk might fit into the more general program. From day one of quantum field theory, we are very used to using zero-form global symmetry and its associated symmetry codimension 1 defect to constrain the dynamics of quantum field theory. More recently, we have witnessed a lot of development on applying the higher form global symmetry and their associated higher codimension defects to constrain the RG flows and all other observable in quantum field theory. These constraints are typically more useful in higher than 2 dimensions, where the higher form global symmetries become more non-trivial. Today, we would like to take an orthogonal direction. This viewpoint was also advocated in a paper by Laksha and Yuji. We will stick to 2 dimensions, 1 plus 1 space-time dimensions, but we will focus on the non-symmetry codimension 1 topological defect and see how they can be used to constrain the dynamics of quantum field theory. Codimension 1 in 2 dimensions means they are lines. So the main player for the talk today will be non-symmetry topological lines in 2D CFT. So first, let me present the theorem. In 2 dimensions, if certain, and I will explain certain in the rest of the talk, if certain non-symmetry topological line is preserved along an RG flow, then the IR theory cannot be trivially gapped. By trivially gap, I mean a gap phase with a unique vacuum. This is similar in spirit to 't Hooft anomaly matching. Typically, if you have an anomaly for a global symmetry in the UV, then in the IR, the theory cannot be trivial because it has to match the anomaly in the UV. But in this case, we don't have any global symmetry. Instead, what we have is a non-symmetry defect in the UV, which is preserved along the flow. So let me start with some basic property of topological lines. Well, the first property is obvious. They are topological, meaning that all physical observables should be invariant under continuous deformation of the topological line if they don't pass through any local operator. This in particular means that they commute with both the left and the right Virasoro algebra in 2D CFT. This is the most important property of topological line that distinguishes itself from the conformal line or the more general line defect. The second property is the notion of defect Hilbert space, which I'll denote by H sub L. So imagine we quantize the 2D CFT on a red spatial circle here, and we have a topological line that intersects with this spatial circle at a point. The intersection modifies the quantization and therefore give you a different Hilbert space than the Hilbert space of local operators. A priori, this defect Hilbert space might not be isomorphic to the Hilbert space of local operators. And it's just some additional data that you should study when studying a CFT. Following from the topological property of the topological line, the defect Hilbert space has to fall into representation of both the left and the right Virasoro algebras. This in particular means that when we decompose the Hilbert space into representations of Virasoro algebras, the multiplicity has to be an integer. And that turns out to be a positive integer, And that turns out to be extremely strong constraints on what a topological line can exist in a given 2D CFT. The third property that I will need is action on the Hilbert space. Given a topological line, it naturally gives rise to a map from a local operator to another. The map is simply given by encircling the local operator by the topological line, and you shrink the topological line. And that will give you another local operator, phi prime. Since the line is topological, this action will preserve the conformal weights H and H bar. In the symmetry case, this action will implement the symmetry transformation and will, by definition, be invertible because every group element has its own inverse. But for more general topological line, the map might not be invertible, and that's the signature of having a non-symmetry topological line. In an RG flow, a topological line L is said to be preserved by the relevant deformation phi if they commute with each other, namely if the topological line doesn't really feel the relevant deformation. This is the natural definition that generalizes the notion of a global symmetry being preserved by a relevant deformation. When we turn on the relevant deformation, we imagine we insert the operator phi everywhere on our space-time. If the topological line does not commute with the relevant deformation, the topological line will cease to be topological and it is broken. But if they commute, the line will be preserved along the flow and it's still a topological line in the IR. One final important characteristic of topological line is its vacuum expectation value. Here we assume that the theory has a unique vacuum, which will be denoted by 1. That will be the assumption we take to be about the UV-CFT. And then the VAF is defined as the eigenvalue of the topological line acting on this vacuum. In the case of a symmetry line, since the vacuum is invariant under the global symmetry, so by definition, by assumption, the VAF has to be 1. I have to say that in the case when there's a 't Hoof anomaly, this definition needs to be refined a little bit. But I will not talk about the case of 't Hoof anomaly today, so I will stick to this slightly sloppy definition. However, for more general topological line, this VAF might not be 1. And that's one diagnostics of whether a line is a non-symmetry line or a symmetry line. One important property of this VAF is that it's RG invariant. There are different arguments why it should be RG invariant. The physical argument is just that the topological line is topological, so it doesn't really depend on the scale. Therefore, if it is preserved along a flow, the VAF should not change. There are more rigorous arguments basing on studying the fusion and the crossing relation of the topological lines. And there's a rigorous mathematical theorem that can tell you the VAF will not be modified under the RG flow. But I will not present those arguments in the talk today. So those are the abstract formal properties of topological lines. Now let's move on to examples. So consider diagonal rational CFT. In any diagonal rational CFT, there's a simple class of topological lines, sometimes called the Verlinde lines, that are in one-to-one correspondence with the primary operators in the rational CFT. Those Verlinde lines will commute both the left and the right chiral algebras. So for each primary operator, there's a corresponding Verlinde line. The action of the Verlinde line on the local operator is completely determined by the modular S matrix. For example, in the 2D Ising CFT, we have 3 primary operators: the identity, the energy operator, and the spin field. Each one of them corresponds to a topological line, which will be denoted by I, L epsilon, and L sigma. The line I is just a trivial line. That just means that we don't have a line at all. The L epsilon line is a Z2 line. Namely, it's a symmetry line associated to the Z2 global symmetry. So it's a symmetry line, and its VAF is 1. In the critical Ising model, we know the only global symmetry is Z2. But we have already identified the trivial line and the Z2 line. So the third line cannot be a global symmetry line. In fact, it's a duality defect that implements the Kramers-Wenier duality, aka the older-disorder duality. And its VAF is square root 2. This can be determined from the modular data of the Ising CFT. This is perhaps the simplest non-symmetry topological line in 2D CFT. So let's take a closer look on how these lines act on local operators. The L epsilon line, as we say, is the Z2 line, so it implements the Z2 global symmetry. It leaves the identity and the energy operator invariant, but flips the sign of the spin field. On the other hand, the non-symmetry topological line, L sigma, it acts on the local operators in a funnier way. The most glaring difference between this case and the previous ones is that the L sigma annihilates the spin field. It gives you 0 on the right-hand side. This in particular means that the action on the Hilbert space of local operator is not invertible. And as we say before, that's one signature of a non-symmetry line. So now let's move back to the theorem. In 2 dimensions, if a non-symmetry topological line L, whose VAF is not a non-negative integer, is preserved along an RG flow, then the IR theory cannot be trivially gapped. This property is the certain that I was referring to earlier. There are several remarks that are in order. First, we assume the UV CFT has a unique vacuum. Therefore, we can define the VAF unambiguously. When there is such a non-symmetry defect that's preserved along the flow, then by the theorem, one logical possibility for the IR theory is a gap phase with degenerate vacua. In that case, the degenerate vacua might not be consequences of spontaneous symmetry breaking. Rather, they are acted non-trivially by the non-symmetry defects. So if you wish, you can think of it as a spontaneous non-symmetry breaking. And also, as I mentioned already earlier in the talk, this is similar in spirit to the Tehuft anomaly matching. The IR theory has to be non-trivial to match certain degrees of freedom in the UV. In this case, it's the non-symmetry line in the UV, which is preserved along the flow. So now let's try to prove this theorem. We will prove by contradiction. We will assume that IR theory is trivially gapped. In other words, we will assume the IR Hilbert space of local operator consists of only one operator, the identity. And then let's do some calculation in the IR. Let's consider the torus partition function of the IR theory with the topological line inserted horizontally at a constant time slice. This partition function has the interpretation as the trace over the IR Hilbert space of local operators, with the line acting on each state. By assumption, in the IR, there's only one state, the identity, which comes from the UV vacuum. So the trace collapses to only one state, and it picks up the eigenvalue of the topological line, which is by definition the VAF of L. We can do this calculation slightly differently by rotating the figure by 90 degrees. But now this calculation has a totally different interpretation. Now the line intersects with what we call the spatial slice, and therefore modifies our quantization. And this calculation has the interpretation as taking the trace now over the defect Hilbert space, which is not a priori the same as the Hilbert space of local operators, and with identity inserted in the trace. This follows from modular invariance in 2D CFT or TQFT. A priori, we don't know much about this defect Hilbert space. But for it to be a sensible Hilbert space, the number of states better be a non-negative integer. That much we know. But on the other hand, by assumption, the VAF of the line is not a non-negative integer, and therefore we reach a contradiction, and hence we have proven the theorem. Let me comment on how to circumvent this contradiction if you do not assume there's the vacuum is trivially gapped. Suppose the vacuum, suppose there are degenerate vacua, then the upper calculation will receive contribution from multiple terms, and those numbers might add up to be a non-negative integer. Let's apply this theorem to some examples. Naively, you might think we can try to apply this theorem to the critical Ising model, where there's a L sigma non-symmetry line. But in that case, both the energy operator and the spin field relevant deformation, they break the L sigma line. So there's not much we can say to test the theorem. So we have to move one theory higher to the next non-trivial unitary minimal model, the tricritical Ising model. In the tricritical Ising model, we can turn on the subleading thermal deformation epsilon prime. And by studying the modular data of the tricritical Ising model, you can see that a non-symmetry topological line whose VAF is square root 2 is preserved along this flow. Square root 2 is not a non-negative integer, therefore by our theorem, the IR theory cannot be trivially gapped. In fact, this flow has been studied by people long ago. For one sign of the coupling, this flows to the Ising CFT. For the other sign, it flows to a gap phase with 3 degenerate vacua. So in this simple example, it actually realizes the two logical possibilities of a phase that's not trivially gapped. Let's consider a second example where we deform the tricritical Ising model by the subleading magnetic field. In this case, maybe I should also mention that for this sign of the coupling, this non-symmetry line whose VEF is square root 2 that's being preserved along the flow becomes the L sub sigma non-symmetry lines that we talked about earlier in the Ising model. If we turn on instead the subleading magnetic deformation for the tricritical Ising model, then one can see that a non-symmetry topological line whose VEF is the golden ratio now is being preserved along the flow. And therefore, by our theorem, the IR theory cannot be trivially gapped. This flow has also been studied by people before, and it was shown that the IR is a gap phase with two vacua. It's interesting to notice that in this case, the Z2 global symmetry in the tricritical Ising model is explicitly broken by the magnetic deformation. So this twofold degenerate vacua are not consequences of the spontaneous breaking of any Z2 global symmetry. Rather, these two vacua are acted non-trivially by the non-symmetry defect whose VEF is the golden ratio. So in a sense, it's a spontaneous non-symmetry breaking. So these are, and in this case, and also in the previous case, just by knowing that we have this non-symmetry topological defects that are preserved along the flow will help you completely determine the IRTQFT. You can use the defect data to determine all the bulk OPE coefficient and the OP coefficient between the bulk operator and the defect operator in the IRTQFT. So let me give some concluding remarks. So we are very used to the power of symmetry, where when global symmetries has 't Hooft anomaly, it's very powerful in constraining the RG flows and other dynamics of quantum field theory. In the talk today, I would like to I discuss the power of non-symmetry instead. There are some codimension 1 topological defects that are not associated to any global symmetry. And these non-symmetry topological defects are equally powerful, if not any powerful, in constraining the dynamics of quantum field theory. In particular, we prove a theorem that if certain non-symmetry topological line is preserved along a RG flow, then the IR theory cannot be trivially gapped. And sometimes the consideration of the topological lines and modular invariance will completely determine what the IRTQFT is. And here's a few outlook. So given this more generalized picture for the topological line, it's natural to ask, if I hand you a set of topological lines that obey the consistent fusion relation and crossing relation, can they always be coupled to a non-degenerate vacuum? In the symmetry case, that would be analogous to saying something is anomaly-free. If they can be coupled to a non-degenerate vacuum, how many different ways? In the symmetry case, that would corresponds to classifying the SPT phases, the bosonic SPT phases, in 2 dimensions that's given by the projective representation or in the case of finite. And more generally, it's not even obvious to me that if I hand you a set of consistent topological lines, is there always exist a topological quantum field theory or even a CFT that realizes these topological lines? And the other interesting future direction is that there are also these non-symmetry codimension 1 topological defects in higher dimensions, higher than 2. The simplest example that I know of is in the 3D U1 at level 8 abelian Chern-Simons theory, where there's a non-symmetry topological surface defect. And it would be interesting to see how one can apply this non-symmetry codimension 1 defects in higher dimensions to constrain renormalization group flows or check-in duality. And I'll end my talk here. Thank you.
Thank you very much for your nice and clear talk. Questions?
So in formulating the condition that this defect is preserved under RG flow, important one was its commute with marginal perturbation. But So that would not apply if there is a higher codimension defect. So would there be no analogous statement for higher codimension, or would there be always one?
Or, oh, you mean if in higher
Higher.
dimensions?
Right. Higher
What's the
codimension.
so in let's see. So in 2D, higher code dimensions can only be local operators. Yeah. So then I don't see an obvious notion of being
But in
preserved
higher
of a
dimension,
local
there are a
operator.
variety of
In
codimensions.
higher dimensions, so let's say it's in 3D, then you are asking if I turn on a relevant deformation, for example, can a line defect be preserved or not? Yeah, I don't know how to generalize that notion directly to the to higher code dimension.
Other questions? Yeah.
If you have two of these non-defects that don't commute with each other, so that you move, when you move one through the other, you get something else. You get something like some generalization of an algebra.
Well, so the most general theory that characterized the algebraic structure between those defects is first of all, there's a fusion between lines. So you can ask what happens if you bring two lines together, and that will give you the fusion algebra. And more generally, there's a crossing relations between the lines, and that's classified by the fusion category. No, it's not. Yeah. I think that's an excellent question. So in the talk, I only mentioned the construction two-dimensional rational CFD, where we kind of cheated using the modular invariance and the modular data. But there's a more, let me give you just one example where you can also identify the non-symmetry defects, at least in 2 dimensions. So in 2 dimensions, say if you have a non-abelian global symmetry that's not anomalous, then you can orbifold that symmetry. You get a non-abelian orbit. Then the Wilson lines of that orbifolding will, in the case when the finite group is non-abelian, will give you non-symmetry defects. So that's a very Lagrangian explicit construction for non-symmetry lines, at least in 2 dimensions. In higher dimensions, I don't know what would be a general Lagrangian way to look for such defects. In that case, well, the short answer is I don't know. And in the 3D example I mentioned, the non-symmetry surface topological defect actually has more to do with different modular pairing of the 2D chiral algebra. It has less to do with the notion of 3D moduling. Yes.
Okay, let's see if there's one more question or remark.
So you mentioned in passing that the reason why these don't form a group is because they're not invertible. What's the idea?
Yeah.
So that means that as operators on the Hilbert space, their states they annihilate?
There are local operators that...
There are states in the Hilbert, say on the circle.
Yes.
We
Yes.
consider this guy going around the circle, then
Yes.
there are states which are annihilated. Oh, so you say that's just some local operator that it moves through.
Yeah. For example, you can create a state by this spin field, and this line will annihilate such a state.
Yeah, but I guess with ordinary symmetries also there are operators that are neutral symmetry. So.
Being neutral is different than saying that it annihilates.
Yeah, exactly. Yeah.
Being
invariant
is saying that it's 1.
It gives 0 on the operator.
Yeah, it's 0.
Okay, that's very weird. Yeah.
All the symmetry lines are associated to the group elements, not the algebra element.
Right. 0, yeah, I guess that's really the...
Yeah. I should emphasize more on this 0 instead of 1.
Okay, so let's thank the speaker again. The next speaker, Kumon Wafa from Harvard. And indeed, I can read the title for you, Cosmology in the String Swampland.
Okay. It's not stable. Okay, it looks good. So first of all, I would like to thank the organizers for organizing this wonderful conference in such a beautiful place, and I'm grateful for them inviting me to give a talk here. I'm going to talk about cosmology and the string swampland, which is a talk based on, first of all, I have to get this straight. So it's a talk based on two papers. One of them is actually just came out with Georges Obi, Hiroshi, Lev Svodinenko, and myself, and also the other one, which is going to come out in a few days, hopefully with Pratik Agrawal and Georges Obi and Paul Steinhardt. So, so the plan for my talk is, first of all, I want to discuss the evidence we have for the existence of the Sitter space. And I motivate discussion based on observation, and then I talk based on this discussion a new swampland condition, which is a lower bound on the gradient of a potential for scalar fields in quantum theories of gravity, with bound being proportional to V itself with some positive constant. And then I talk about cosmological implication of two swampland criteria for past, present, and future of the universe. One is this criteria, and the other one is a criteria on the bound of the range on the scalar fields. So before I start with the discussion, I should point out that this talk is based on really speculation, but I hope that the speculation has a strong motivation in terms of possible observation in the real universe, which is what we hope to do in string theory. Of course, the rain during the lunch was not a promising sign. So hopefully this will So hopefully this will not be in that category, we'll see, but at any rate. So it is speculation, but I'm going to shamelessly discuss it nevertheless. I think we need discussion which hopefully connects string theory to observed universe, and this is in that hope, in that direction. So I hope you allow me to entertain this speculation here. Okay, so why the sitter? Well, the answer is because we live in one. If I ask this question to any of you guys, most probably the answer I would get would be something like this. We live in one space called the sitter. So your theory better give that to us, otherwise your theory is wrong. That's the reaction most people, including I, would have had. Because we say, well, we have a positive cosmological constant, so you have some kind of potential. We know in string theory there's no free parameter, so there's got to be some potential of some fields with a minimum, or at least a local minimum, at some positive value, which is our present cosmological constant. This is the present picture of how we try to connect string theory to our observed universe with the lambda, which is very small. Question comes, why not rolling scalar potentials a la quintessence models? Why don't we imagine having a situation like the cosmological constant on a rolling potential instead of having a fixed value? Well, there are various arguments and there are various motivations why people do not like this scenario, and I want to review those arguments. First of all, the scalars will be useful if they couple to something, and typically in string theory, we are very sympathetic to that. If you have a field, it's not going to be possible, or we don't know examples where it doesn't couple to anything. It better couple to something, and therefore it's natural to think that observables will be affected. For example, you would think that the fine structure constant will vary. But there are strong bounds on these things, like the variation of the fine structure constant the percentage change of it from z equals to 1 to now is less than 10 to the minus 6, which is extremely tiny. So this suggests that if there is such a thing, this scalar is not changing these observables in any way. Another problem is that if you have this scalar field, then the coupling, and if it couples to the matter field, it gives rise to new forces between the matter field. This is almost like a very light scalar field, and you get some fifth force. And the fifth force, if you look at astrophysical observations, it will give rise to apparent violations of equivalence principle, because there will be extra force other than the gravity in the game, and so you will get new things. And there are strong bounds on the apparent violation of the equivalence principle. So there are also strong bounds on the fifth force. So these are two arguments leveled against this picture. But from a string perspective, these do not look like good arguments. So first of all, it's true that scalar fields should couple to something strongly. That string theory tells you that. But that something may not be the standard model. So it could be that we have a compact manifold. The standard model is coming from a local region of the internal geometry, and then there's some other sector, the dark matter, for which the scalar couples strongly. So in this case, we could say that if we are in a rolling situation, that rolling one anticipates dark matter. So it's a prediction of dark matter instead of saying it's a negative thing. So it's the exact opposite. But there is another strange feature of quintessence models. Not only the value of the cosmological constant is small, 10 to the minus 122, but also if you want to make the quintessence models work in Planck units, the gradient should be bounded also by about 10 to the minus 122. This looks like double fine-tuning. However you want to fine-tune V, you have to, in addition, fine-tune gradient of V. So the easiest answer you would say is 0. Why do we go to such a distance? Unless somehow the gradient of V and V are somehow related. If there is a natural bound of the form gradient V of proportional to V, this alleviates this double fine-tuning. Unlike ADS, constructing de Sitter vacua, even metastable ones in string theory seems very difficult. Now here, I want to make clear what I mean by this. I do not mean trying to get the observed universe in 4 dimensions with standard model, with de Sitter, etc., etc. That's a tall order. Rightly so, people will say, this is a hard thing to do. How do you expect me to get the exact answer? No, I'm not asking that. I'm saying there's no single example of de Sitter anywhere in any dimension, in any string compactification, which is simple. So in other words, take 10 dimension, 9 dimension, 8 dimension. No, I don't care about standard model, nothing. Just give me one example of de Sitter which is trustable that I can actually compute and check. We don't have any examples. Well, despite this, there have been heroic efforts, notably the KKLT and similar follow-ups. There have been attempts and there are proposed scenarios of how you can achieve this. And I think there are also criticisms leveled against them. So I think they are at the level of proposed scenarios for construction, not rigorous construction, so we do not know the status of them yet. It could be that this is true and this scenario comes to fruition, so I cannot rule that out, and we do not know that. But given that we do not have a strong, sure way to assess that, it is worthwhile to contemplate the opposite. In fact, if you want to construct de Sitter vacua, one needs to do something at least a little exotic. For example, Maldacena and Nunes give a simple no-go theorem in the limit of M theory supergravity. So you take the M theory in supergravity limit, where you ignore the higher curvature corrections, and in that context, they simply and beautifully show that there is no de Sitter in M theory vacua, no matter what dimensions you take. This, of course, does not mean you can never get de Sitter from M theory, because you can have high curvature corrections or situations where the curvature of the manifold becomes Planckian in M theory units. So that does not prove it, but still, the simplest thing that you might think does not give you a de Sitter vacua. So let us dare to ask, what if there are no critical points of V with positive value? If so, the next natural question is how close we can get to gradient of V to 0. If gradient of V is 0 is not achieved, maybe there's a bound away from 0. Perhaps gradient of V is bigger than a universal constant, which is positive. This cannot be. For example, take a theory which is supersymmetric in, for example, Calabi-Yau compactifications. And consider one of the massive fields. Sometimes these have massive fields. You go to the massive field, and you can take a wave of the field near zero, and this gives you a potential which can be arbitrarily close to zero. So that's not true. So this cannot be a correct criteria. So one can instead consider a bound of the form gradient of V is some function of the scalar fields, and perhaps a natural choice for F would be the potential itself times some constant, some positive constant. So we contemplate the possibility that we have a bound that the norm of gradient of V is bounded by a positive constant times V, where C is some number of order 1 in Planck units, presumably a universal number, which may depend on dimension, and of the form of the gradient of V bigger than or equal to C times V. So let's make a check of this statement. So gradient of V is bigger than or equal to CV is trivially satisfied when V is negative. So for supersymmetric vacua, we know that V is less than or equal to 0, so therefore, at least for those, there's no contradiction to having gradient of V being equal to 0. So this is fine with supersymmetric vacua, we know. So even, also it's trivially satisfied for supersymmetric examples with 0 cosmological constant. If V is 0, you could have some flat moduli, but that corresponds to the equality part of this, this relation, so that's also fine. So then we ask, how about positive value of V? So what is the right way to think about this band when V is positive? So let us start with the supersymmetric case with 0 cosmological constant. For example, type 2 strings on Calabi-Yau, let's say. And then we want to deform the theory. Well, how do you deform the theory? Well, you just give a wave to some operators, which in the context of this theory would correspond to, and if you want to go away from supersymmetric one, it means that you're giving wave to some massive fields. So basically, you can parameterize the deformations away from the supersymmetric one by deformations of the type of the potentials of the form 1/2 m squared phi squared for phi near 0. So if you compute gradient of V over V for these examples, you get simply 2 over phi, and this is this, as you can see, is bigger than order 1 for phi near 0. Of course, when phi is too big, you don't trust this description. In fact, you believe that phi is of order 1 in M Planck. You definitely won't have such a simple form, and you have all these other issues with getting the tower of light states. So this actually fits beautifully with the statement that the range of the fields cannot be that big for a given effective field theory. One can consider M theory in the supergravity limit and consider compactifying on to d dimensions on an arbitrary 7 manifold to 4 dimensions. So you go from 11 to 4 dimensions, pick your 7 manifold of your favorite type with arbitrary metric and arbitrary g-flux. The only thing I want to assume is that the supergravity approximation is valid. In other words, I'm not considering a situation where you have singularities in geometry or you have curvatures of the order of M Planck in G or R, so you're restricting to that kind. From the viewpoint of 4 dimensions, all the choices of the metric and the fluxes would be these scalars. So you have a potential as a function of infinitely many scalars which parameterize for a given topology of the manifold, the metric and the fluxes. Huge potential. Now, if we didn't know any better, we would have said, of course, there's going to be somewhere a critical point for that V. It's hard to believe there's no such critical point for positive V. But that's precisely what Maldacena and Nunes show. For positive V, there is no critical point. So sometimes a reasonable looking statement that if I had just told you, take a generic V and find the critical point is not correct. Okay, this is an example. And this is the no-go theorem for Maldacena and Nunes. So we shouldn't necessarily believe our intuition of what is natural is necessarily the correct one. In fact, the Maldacena-Nunes no-go theorem can be strengthened. Suppose you compactify M theory to d dimensions, one can easily show that upon using just the very boring volume rescaling, that gradient of V over V is indeed bounded by a constant of order 1. No matter what manifold you choose, no matter what metric you have, etc. So for any 7 manifold, any metric, any flux, you have a bound. So what do we say? Well, we say we try to violate it by Planckian corrections. That's what we are saying. For M theory, it's impossible to do it if you just take supergravity approximation. One-line argument, nothing fancy. Now, for d equals to 4, the bound you get from this is 1.6. And this is indeed realized in the ADS 4 times S7 example. If you go away from the minimum as a function of the radius, if you look at the potential, if you go away from the minimum, which is the negative v, to the positive values, sufficiently close to the origin, you find the slope indeed goes like this limit. So these values are actually realized in actual compactifications. If we assume the strong energy condition, which of course we know it's not true in general, or more precisely, if we consider compactifications respecting the strong energy conditions, you get a bound of this form. If you start with capital D dimensions, assuming strong energy condition is correct, going down to lower dimension D, you get grad V over V bounded by this number. And if you compactify, if you use the null energy condition, similarly, again, we know null energy condition is not necessarily true in string theory. There are objects which violate it. But if you consider compactifications respecting it, you get a bound like this. Again, you get numbers of order 1. So if you go down, for example, to 4 dimensions from 10D, you get number of order 1.2 for this bound. So how about other examples? Well, there is actually a non-supersymmetric example which does realize a positive cosmological constant. This is from old days, and I think the younger group here may not even be aware of this. This is called the O16 times O16 strings. It is a non-supersymmetric, non-tachyonic theory in 10D. And at weak coupling, you can compute the cosmological constant as positive and in fact rolls down like this. So you can compute it for that example again. Grad V over V is some number like 5 over root 2. So there are examples which naturally realize it with nothing fancy in 10 dimensions. Also, extending an argument of Hertzberg et al. And also Rassi et al., one can show that if you compactify type 2A or type 2B from 10 dimensions to 4 dimensions with arbitrary Ramond-Ramond flux and with OQ and DQ branes turned on, but only for a fixed Q, then for almost all these cases you get bounds of the type I just told you, including negative O branes, by the way. So this shows that for a large classes you get no-go theorems. Now this does not cover all cases, as you can see, and I'm also assuming that only a very specific Q is turned on, so I'm not turning on all possible OQ and DQ branes. But there is very little work involved in showing this statement, I'm trying to say. It's very boring little rescaling of the volume and the coupling constant. That's all that goes into these arguments. Nothing fancy. Now one can try to do more fancy things and perhaps get other things, but in other words, when these are empty, it doesn't mean that this goes to 0, but we just don't know how to find a bound. So the upshot is that the conjecture is not unreasonable with C of order 1 in Planck units. Okay? Well, this also makes quintessence more natural because now V prime of order V is not double fine tuning. It's very natural in the context of string theory. So now we don't have that objection. The two natural objections or 3 natural objections raised against quintessence are alleviated in the context of string theory if this Swampland condition is correct. So what are the cosmological implications? Well, so there's this bound I told you about, grad V over bigger than or equal to C times V. There's another bound which is discussed a while back, which we proposed with Hiroshi, where the range of scalar fields for a given effective field theory that we write down is bounded by something of order 1 in Planck units, which I call now here delta. And we believe that C and delta are numbers of order 1 in Planck units, though we don't have precise numbers here. So let's assume that these are strict true facts about quantum gravity and see what consequences they lead to. And well, there are 3 consequences we can contemplate: the past, the present, and the future of the universe. So let's go to the past. Early universe, inflation has mild tension with these criteria. In fact, the constant C that I talked about is related to the slow roll parameter in this form. And the current observational bounds on the B mode lead to epsilon less than 0.004 and C less than 0.09. However, actually, the textbook models of inflation, when combined with the spectral tilt, gets ruled out. So among the ones which are not ruled out and which are favored by some inflationary models are the plateau models. And in those cases, one finds C is less than 0.02. Well, okay, so you could say this is order 1 number or not, I don't know, so I leave that to your judgment, but at any rate, this number is getting to be a little small compared to the examples at least I showed. Moreover, the number of EFOs being greater than 60 leads to that delta bigger than 5, again in these plateau models. Again, a little too big for comfort. This is, again, not strictly a problem, but it sounds like a little bit of a potential issue coming up. Okay, so that was the inflation, and let's talk about present. So now the fact that we are saying that you cannot be in the metastable de Sitter only allows quintessence models. Therefore, you could ask, what does a quintessence bound give you? So here, this plot here is a function, is a W as a function of Z. So this Z is the usual cosmological Z. W is the one which defines the equation of state for the dark energy component in the universe. So this black line here are the observational bounds between, so the observational bounds are the value of W is between this black curve here and -1. -1 would be the value corresponding to the cosmological constant, where you have a metastable de Sitter, whereas the observational bound are these blacks. If you just take simply a potential of the form V e to the minus C phi, and where C is a constant, you find that if the constant is 0.6 or lower, you comfortably satisfy them, no problem. Amazing that the bound, the experimental bound, gives such a number of order 1 in M Planck. This is remarkable. It's remarkable that the bound we're getting from experiment gives you the bound which is of order 1 in this M Planck units that we are discussing. So it actually reinforces the idea that not only quintessence is not ruled out, but it's actually quite natural in this context. In fact, one finds that there is a universal bound. So this was just this example of this potential. But you could say, well, what about the more general case? You find that this gives you actually the best bound that you can get. And in particular, you can show that it predicts that 1 plus W today is bigger than 0.15 times the square of that number that appears in this swampland conjecture. So, and this CB less than 0.6 is consistent with data. So one way to check would be to compute the W. So this suggests that we should try to continue with the efforts to try to measure W, and there is not theoretical motivation to see whether it's -1 or not. How about the future? Well, if we lived in de Sitter space, the lifetime of the universe before there is a phase transition can be arbitrarily large, because we would be we presumably will be either infinitely stable or maybe some decay in the usual metastable form, but there is no relation between the cosmological constant, this energy, and the height of this barrier. So in principle, the lifetime is completely unrelated to the dark energy or cosmological constant. However, today, the lifetime today is very interestingly related to 1 over the square root of lambda. Now, people say this is the coincidence problem. This is one version of the coincidence problem. Why do we happen to live in an age where this is true? There would have been a satisfactory answer if the age of the universe cannot be much more than that, in which a typical number you sample would be of that order. So if you look at grad V, So if you look at the grad V bigger than V constraint, it's getting exciting here. Okay, I don't know how this works, but okay, I'll do it easily. So we go like this. So what's the future? So we are basically rolling down. We can put a lower bound on the speed of the rolling, the kinetic term of phi today, based on observations. And it's rolling. And we know that grad V over V is bigger than some constant. So therefore, this is going to somehow roll like this, or perhaps cross 0. But this cannot range more than order delta before the effective field theory breakdown with getting a tower of light states, according to the swampland conjecture that we had with Hiroshi. Therefore, we can estimate how long does it take for this guy to roll a distance delta. And you find that the number of Hubble times for this to happen is proportional to delta over C. The delta is that other constant in the swampland conjecture, and C is the constant that I was talking about. So these are both order 1 numbers. and you get 3/2, and this omega is this 0.7, is the fraction of energy in the dark energy. So this number is of order 1, which means the number of E-foldings left over before we undergo phase transition is of order 1 in Hubble time. Therefore, if you sample the time in that scale, it's related to the dark energy. So the statement is that precisely when the dark energy takes over, we're basically about to do a phase transition. That's the nature of this argument. So in other words, it is not a random time we are in. It's about the end of it. So, so the argument uses the relation that if you compute the kinetic term, and if you integrate it, the kinetic term at the kinetic term now, which is x0, which is bounded by experiment, and making sure that this is the total range of the field is less than delta, gives you this bound for the range of the field. So simple argument. So I have run out of time, but let me just say what are the observational consequences. So first of all, it suggests that we should do more accurate measurements of W of Z, and we want to see if 1 plus W is significantly different from 0 today, as we are predicting. The dark sector couplings have been changing over time as they presumably couple to the quintessence field. So observational consequences of these would be apparent violation of equivalence principle in the dark sector, which would be very interesting to detect. So let me conclude. It seems not unreasonable to believe de Sitter is not realizable. So my colleague Hiroshi suggested the double negation. He liked it here. So as you can see, we are very careful here. We do not know. It could very well be that the constructions are correct. So this is would be viewed as a speculation in that case. But it seems like it's reasonable to entertain it. As you can see, it has dramatic consequence, and it's worth exploring. And this gives you some tension with inflation. It's a mild tension. Present epoch must be based on quintessence, and there naturally fits with these ideas. And the universe is about to undergo a phase transition in order 1 Hubble time. And so I think I would say that either a tower of light states will appear or the cosmic acceleration stops. So I will stop here. Thank you.
Thank you very much. I'm sure that there are questions.
If d phi is of order phi, d refers to spatial and time variation, right?
D phi, delta phi is the variation of phi over time, for example.
Yeah. So that means that phi is changing over Hubble, over length time?
It means that the range, so usually we take in the field theories, the range of phi is could be minus infinity to plus infinity. So what we find is that in string theory, for example, in the Calabi compactifications.
No, but you want to consider the case where d phi over is of order
Not phi, if dv, you mean.
dv.
V is the potential for the phis. So V is a function of, V is a potential for scalar fields. The question is, what are the slope for this? What's the gradient of this potential? And does it relate it in any way to the value of V, not phi? Phi is not the issue. So there are two conditions. That was one of them.
Have you explored what happens to fundamental constants as a function of cosmological?
So the statement is that this field would not, if this field coupled to our sector, it would be quite dramatic and it would be wrong, clearly. But as I tried to explain, that's not the necessary situation in string theory. In fact, a very typical example of models in particle phenomenology is that we have a localized sector. If you view this red geometry as a geometry of internal space, the green area is where we get our matter, and this is what happened, for example, in F-theory models in phenomenology. This could be another area. There's a dark matter. Would be, that's...
So you're putting in addition to, so you're still left with the fine-tuning of B, cosmological.
Yes, no, we have not, so absolutely. So we have not solved this cosmological constant problem.
And to deal with this problem, you're putting in another
sector.
Fine-tuning.
Another sector, I would say, which is dark matter.
Yeah, no, I understand. Another sector which you assume by this mechanism or some other is exponentially suppressed.
Yes, exactly.
But that's another potential.
Not so strange in string theory. First of all, we know there is dark matter.
In this.
Yeah, so in other words, if you take the prior, in experimental prior, that there is dark matter and couples weakly to us, this is a very natural picture in string theory, given that.
This is A.
Yes, it's a natural picture.
But what's so this is a way of getting such a suppression. What kind of suppression do you need? to agree with the fact
Yes.
that constants don't change in time. It's one of the arguments against quintessence.
Yes. So usually, for example, in string constructions, you get localized fields like in orbifold singularities.
How this is realized in string theory. What factor do you need?
Oh, 10 to the minus 6. I showed that number before. So here is the change of the fine structure constant, for example, over the period from z to 1. It's 10 to the minus 6. So that's the suppression. It's not infinitely big, but small.
So I appreciate the kind of cautious way that you presented your argument, but still, you focus on these no-go theorems that explicitly exclude orientifold planes.
No, it
give-
included
which
it. Sorry.
give-
No. It included.
The ones which give a dip
No,
in the
no.
M theory does not have these.
No, let me show you. This actually was already done in the paper by Kravchuk et al. As well as by Rassi et al. Here.
No.
The orientable plane are not, with a negative tension are not excluded in this discussion.
But as you also said in your comment there, you didn't include all of the possible.
That's right. Otherwise, I would have given
No.
a proof.
I'm sorry, but you didn't include the leading contribution to the scalar potential in string theory, which is the D minus D critical term, which leads to the original scenarios for de Sitter. There is also a three-dimensional model, which is pretty explicit, that came out in 2010
Yes.
with Shidong and Gonzalo Taroba.
Yes.
So if you have an objection to the details of that, please let us know.
Okay, we can discuss it. But anyhow, I didn't want to get individual models because there are hundreds of people that I would have to respond to. But the main point is not to say they are wrong. I'm not saying you're wrong or they are wrong, but I'm just saying that the possibility, I think going over supercritical dimensions in string theory is debatable, whether that's a good thing to do or not. We have discussed that before.
Well, it's connected to the rest. There's a lot of literature on that by Hellerman and by...
Yes, but anyhow, I don't want to
So
debate.
it doesn't make sense to exclude that by fiat.
No, I didn't
given
exclude it.
that
I just,
is connected to
Eva,
the rest of the theory.
Eva, you might be right. I'm not saying you're wrong. You might be right, but this might also be right.
Just give a detailed reply to the existing models. That's
Sandeep.
Thank you for a very thought-provoking talk. But let me just say, some of the ingredients that have gone into the kind of constructions are generic that Eva was referring to, which are not in your bounds, are generic. For example, quantum corrections. What KKLT actually illustrates, how was the Maldacena-Nunez no-go theorem evaded in KKLT? At root, because quantum corrections were incorporated.
That's a fair criticism. Some people believe, in fact, it's a fair criticism. Some people believe that quantum correction might do the job. It may or may not do the job. My only statement is that quantum corrections typically get dualized to non-quantum corrections. It becomes classical. So it's surprising that in no picture that quantum thing can be seen classically. That's already a surprise. So somehow it should be that in any classical frame, there has to be quantum correction for this to happen. Could be, I do not know, but that sounds exotic, you agree?
Well, I think we have one more question by Greg, and then we have to stop because I
have a much simpler question. So delta V over V has units, and so you said you were bounding it by order 1 in the Planck scale.
Units.
Which Planck scale?
Planck's in 4 dimensions. So
well, but why not the 11-dimensional Planck scale?
No, in each dimension. So first of all, in each dimension, there's a bound in that dimension. The constant will depend on dimension. That's the first statement. So that's, in fact, let me bring it. So,
but these differ by functions of the moduli.
No. So you're an Einstein. No. You're an Einstein frame. You go to the Einstein frame. It's unambiguous statement here. You always are an Einstein frame. There's no ambiguity in the definition of the distance. And one other thing I forgot to mention.
But if you start to decompactify, then that's going to change, right?
In each, for a given effective field theory, so that's related. That's precisely why the range of the field is bounded. In other words, as long as you have an effective field theory which is valid, that means there's a bound in the range of the fields. One thing I forgot to mention is that, so to an effective field theorist, this doesn't look right. To a field theorist, we say the range of field could be arbitrary or the grad of V could be anything. But if you restore, as Greg is suggesting, M Planck here in the discussion, the M Planck will go down in the denominator. And if you take m prime to infinity, there's no bound. So precisely when you decouple gravity, there is no bound. So this is consistent. Any swampland criteria should be trivially satisfied in the field theories that we know, and this does satisfy that at least.
I think it's very good that we have this discussion, but I think we also have to go on. So thank you very much, Kumrun, again.
Thank you.
So we come to the third speaker of the session, Douglas Stanford. So now the title is a semi-classical ramp in the SYK and in gravity.
Okay, this on? Great, thanks a lot, it's a pleasure to be here. This talk is, sorry. Uh-oh. This talk is based on work with Steve Schenker and his student Phil Sod. Yeah, I'd better get this right. Okay. Now, you know, I don't mind holding it. How's that? Think it's better? Yeah. Okay. So this talk is based on work with Steve Schenker and his student Phil Sod. God, I feel like such an amateur. How do I do next? Okay. All right. Let me start this over. It's a real pleasure to be here. This talk is going to be based on work with Steve Schenker and his student Phil Sod. So in a black hole geometry, correlation functions of simple bulk fields separated in time seem to just decay with the time separation. Roughly, the reason is that the quanta can fall into the black hole, but they don't come back out again. However, ADS-CFT interprets such observables as standard thermal correlation functions, and we can use the Hilbert space formalism for the quantum mechanical theory to write this type of correlation function as a double sum over the energy spectrum of the theory. So here we have such a sum, and the time dependence here is just in these oscillating phases. And it's a simple property of functions of this type that they can't decay to zero asymptotically at large time. So Maldacena pointed out that this is a sharp tension with the naive gravity picture, and it's become known as Maldacena's version of the black hole information. Now, the key actors in this story are these oscillating phases. Matrix element squared of the operator phi isn't so important, so we can focus on a slightly simpler quantity, this one, where we just study the double sum over the oscillating phases. If we like, we can write it as the absolute square of an analytically continued partition function, z of beta plus it. Now, this quantity has a name. It's known as the spectral form factor, and it's been studied for decades in the context of quantum chaos. Just as an example of some numerical data, the SYK model with 34 ionofermions, this is some numerical data. So this is a log-log plot. The y-axis is the spectral form factor, and the x-axis is time. The red curve is a plot for a single realization of the SYK model. I'll define that in a second, but it's a disordered theory, and that's for a single realization of the disorder. The black curve is an average over 90 realizations of the disorder, and it's getting somewhat smoother. If we actually considered the strict disorder average, it would be a smooth curve. So there are sort of three qualitatively different regions of this curve that have been labeled slope, ramp, and plateau. In the slope region, this function is indeed decaying, and it has a check mark next to its name because it can be understood, has been previously understood analytically. It starts out large of order e to the 2 times the entropy, but it decreases with time. In the ramp region, the smoothed function, the disorder average of the function, is just growing linearly in time with an order 1 coefficient. And eventually, at late times, the function plateaus at a value that's exponential in the entropy, is large but much smaller than the initial exponential in twice the entropy. So the ramp and the plateau didn't have analytical explanations, but they have sort of a moral explanation, which is that you would find similar behavior in the context of random matrix theory. So if we replace the Hamiltonian by just a random matrix. And the reason is that the ramp and plateau are probing the statistics of the energy eigenvalues at distances that are relatively small compared to the full size of the spectrum. And in a wide variety of chaotic quantum systems, it's expected that the statistics of such energy eigenvalues agree with that of eigenvalues of random matrices with the right symmetry class. So in other words, random matrix universality sort of explains the ramp and the plateau and predicts that this structure should look somewhat similar for many systems, not just SYK, but many systems, including, for example, n equals 4 super Yang-Mills, and by extension, black holes. So what we would like to do is understand more of this curve for a black hole, in particular this ramp and plateau region. Now, we can place that problem in a slightly more general context as follows. Some people of my generation, I guess, have been brought up to think of quantum gravity, at least in anti-de Sitter space, as a collective field description of a large N holographic CFT. So a more general problem would be to find this ramp and plateau using the collective field description of some large N quantum model. So in particular, the way that we want to do the computation here to find these features is important. We want to use the collective field representation. We want to find these features somewhere in the functional integral over collective fields. Using the Hilbert space, or even using the fundamental degrees of freedom of the model, would be considered cheating. And certainly, exact diagonalization numerics would be cheating. Okay, so that's the challenge that we're going to discuss in this talk. So the first 2/3 or so are going to happen in the context of the SYK model. Now, this is a model, it's a quantum mechanical system of n Majorana fermions interacting in groups of 4 with a random antisymmetric tensor J of couplings. And we can write the spectral form factor. Let's start with the case with beta equals 0 using 2 replicas of the system. So we have these 2 factors of the partition function, trace e to the minus IHT times trace of e to the IHT. We represent those 2 traces as 2 systems, L for left and R for right, 2 copies of the SYK model. And it's important that both of them will have the same random couplings. But we're going to consider the disorder average of their product. The disorder average means a Gaussian integral over these couplings. And it's denoted with those angle brackets. Now, a nice feature of the SYK model is that disorder average quantities can be computed exactly by a theory of collective fields. Collective fields are called G and sigma. Now, sigma is a Lagrange multiplier, and it's better to just think about G. So let's discuss the meaning of G. So G is a bilocal field. It depends on a pair of times. It also has a pair of replica indices, I and J. So I and J can be either left or right for the 2 systems, L and R. And G is equal to an average of the fermion, a bilinear of the fermions. This diagram on the bottom is supposed to sort of explain what it does. The 2 vertical black lines represent the time evolution of our 2 replicas, the left and the right systems. The circles at the top and bottom represent the anti-periodic identification we do to compute the traces. And so we see here, for example, GLL as a function of 2 times would tell us about the correlation of fermions at 2 different times in the left system. GRR would be on the right system. And the off-diagonal term, GLR, tells us about correlations between fermions on the left and right at different times, T and T prime. Okay, so the nice feature of this collective field description is that if n is large, then the path integral on the top line of the slide here would be strongly peaked around a saddle point. And for many quantities, we can get by with studying a saddle point and small fluctuations about it. And actually, the conclusion of this talk is going to be that both the slope and the ramp can be understood by saddle points, although we believe that the plateau cannot be, at least not simple. Okay, so let's start. So the action here in terms of these G and sigma fields has this following non-local and bilocal form. It's similar to the G and sigma action for the standard SYK model. The specific formula isn't going to be too important, but I wrote it up there just to make things explicit. In order to write the saddle point equations simply and solve them, we make an ansatz that the G and sigma fields should depend only on the difference of the two time arguments. In other words, that we should have a time translation symmetry. And after we do that, we get the two equations on the bottom. The left one is expressed in frequency space. Omega n is a Matsubara frequency, and the right one is in time space. These functions with hats on top of them are the functions of a single time that the bilocal fields are expressed in terms of. Okay, so now let's discuss a couple of types of solutions for the slope and for the ramp region. Small. So this is a plot of a numerical solution to those equations. They can be solved just by iterating them. And the x-axis here is time, t, which runs from 0 to capital T. This parameterizes the time on a circle. So in particular, when t is close to 0 or when t is close to big T, then the time arguments of the fermions are close to each other in a circle. This is for a solution where g left right is equal to 0. In fact, g left right is always pure imaginary, so the imaginary part here is 0, which means that g left right is equal to 0. And in that case, the saddle point equations decouple into separate equations for the variables in the left system and the right system, describing the correlations just within those two systems, but no correlation between them. Okay, and it turns out that the left-left and right-right solutions are given by complex conjugation. So this is a plot of those solutions. Now, for large time t, these solutions cross over into the so-called conformal limit of SYK, and we can give analytic formula for the solution. That isn't too important. A more important feature is that the action approaches a constant for large t, and n times the action approaches minus 2 S naught, where S naught is the so-called zero temperature entropy of the SYK model. This is just a number that's large, it's proportional to n. So the contribution of this type of saddle point to the functional integral over g and sigma gives something which is large, e to the 2 S naught. And if you study the fluctuations about this saddle point, you find a power of 1 over capital T cubed for large t. So this saddle point here is describing the slope region. It's a very large contribution, but it's decaying with time, 1 over T cubed. Okay, so this was previously understood. But we can also find another type of saddle point. Here's a plot of an example of a numerical solution of another kind, where g left right is not equal to 0. So g left right, the imaginary part, is plotted in the dashed yellow line there, and you can see it's not equal to 0. It's maybe a little bit hard to see based on these plots, but there's a qualitative difference in the solutions, which is that for this correlated saddle point, the functions are decaying exponentially in time, away from 0 and capital T. Whereas in the previous plot, they were decaying only like a power, short times or times close to. Now again, at low energies, one can write analytic formulas for the solution, but what's more important are a couple of properties of these solutions, which we'll discuss in a moment. The first property is that the action becomes 0 for large t. The second property is that there are two zero modes, which we'll discuss. The combination of these two things together gives us the following contribution of this type of saddle point to the functional integral, gives something which is order 1 as a function of e to the n, so there's no e to the n dependence, but it's multiplied by t, which is a factor that comes from one of the zero modes. So this saddle point and the integral of fluctuations around it, including these zero modes, gives a description of the ramp in the SYK. The rest of the talk is going to be about a little bit more detail on this solution, and then some discussion about translating that solution into gravity. So first, we should understand this zero mode. And it has a fairly simple origin. So if we're given a solution to the saddle point equations where g left right is non-zero, then we can find a whole family of them by making a relative time translation between the left and the right systems. So in terms of this g hat variable, we just shift the argument of g left right by a parameter delta t, where delta t represents the zero. So those plots are numerical plots for non-zero values of delta t. You can see that that yellow curve just gets shifted over. This parameter delta t can be understood as a type of Goldstone zero mode for spontaneous symmetry breaking from two independent copies of time translation, one for the left system and one for the right, down to a diagonal subgroup that's preserved by this solution. So the solution that correlates the left system with the right system does so by correlating fermions on the left system with fermions on the right system at sort of the same time. And that breaks the independent time translation symmetries. So we get a zero mode, and the zero mode parameterizes an orbit of the broken symmetry gen. Anyhow, this zero mode is valued between 0 and capital T, because we're living on a circle, and the integral over it gives a factor of capital T. So this is the origin of the linear growth of the ramp region. Now, I just sort of showed a picture of the saddle point, a numerical solution, where we could ask why these solutions exist. Like, where do they come from? How can we understand where they come from? And in order to do that, it's helpful to consider an auxiliary problem. So let's forget for the moment the spectral form factor with these two traces, and consider another quantity, trace of e to the minus 2bh, where b is some parameter with dimensions of length. Now, if you like, you can write that in a sort of crazy way as a trace of a product of 4 factors, where we intersperse e to the minus iht and e to the plus iht between factors of e to the minus bh. And that's trivially equal to the expression on the right, because h commutes with itself. But if we like, we could imagine representing that quantity with a path integral that has sort of a time contour that represents each of those 4 factors. And one can solve the SYK equations for G and sigma, the saddle point equations for the system on this kind of time contour. Now, if we imagine that capital T here is extremely long, then what we can do is we can cut out the region of the solution along the long Lorentzian parts of the contour, and we can use those functions as solutions to this spectral form factor problem with 2 traces. Now, that's not completely obvious because the equations that we're considering are not local equations. But their degree of non-locality is determined by the functions g and sigma themselves. And on this type of time contour, the solutions are exponentially decaying. So the equations are local enough to allow this type of operation. This perspective is also helpful for a couple of other reasons. First, the answer to the first problem there is exactly independent of capital T. And one can use this to show that the saddle point action for this saddle point for trace of e to the minus iht, trace of e to the iht is 0. The second thing it helps us with is to understand the second zero mode that I promised but haven't discussed yet. We discussed the zero mode delta t, but there's another zero mode, and that's just this parameter b, which was an arbitrary length parameter in the construction that we just described. So contributing to the ramp would be saddle points not just with all values of delta t, but with different values of b as well. And this represents something sort of significant, which is that all energies contribute equally to the ramp in the spectral form factor. It's different from in thermodynamics, where because of these huge e to the s factors, particular energies will dominate thermodynamic expressions. Here, in the ramp, we don't have these e to the s factors. So any given energy band contributes the same. And that's what this zero mode B represents. Anyhow, if we want, we can get rid of the zero mode by studying a microcanonical version where we integrate over beta over a contour a little bit to the right of the imaginary axis, defining this quantity y, and this will fix the parameter b in terms of an energy argument for the quantity. So this concludes the SYK part of the discussion. What we're going to do now is try to translate these saddle points into gravity language. So at low temperatures, there's a useful correspondence between the SYK model and Jakiv-Teitelbaum gravity. And we'll use this to get started on understanding what these things could mean in gravity. The Jakiv-Teitelbaum model is a two-dimensional theory of dilaton gravity. And the action consists of these two terms here. The first term is a topological term. It just gives S naught times the Euler characteristic of whatever manifold we're considering, whatever two-dimensional manifold we're considering. And the second term involves the dilaton phi, multiplying this expression r plus 2. The equation for phi sets r equal to -2, and we get a piece of hyperbolic space. This is a theory of ADS2. Now, one way to understand the correspondence between solutions to this model and SYK is that we can match them up by looking at the correlation functions G in the SYK model and matching those to correlation functions of free two-dimensional fermions in the two-dimensional Jakiv-Teitelbaum space. We have free fermions in the bulk. We compute their two-point function and match that to the correlators of fermions in the SYK. So an example of how this works, if we just study a simple quantity like the thermal partition function in SYK, and it's useful to discuss actually a product of two copies of the thermal partition function, z of beta times z of beta, then the fermion correlation functions, G, that represent the saddle point for that quantity, are in correspondence at low temperature to the correlators of fermions on two separate hyperbolic disks. Two hyperbolic disks representing the two theories. So these hyperbolic disks can be interpreted as Euclidean black holes. So this underlies the relationship between the SYK model and two-dimensional black holes. Now, the saddle point that we discussed first, that uncorrelated saddle point, is one for z of beta plus it, z of beta minus it. And in Jakiv-Teitelbaum language, that becomes two separate complexified hyperbolic disks. Okay, so now what we'd really like to do is find a solution in JT gravity that represents the correlated ramp, the correlated solution that represented the ramp. So, okay, these two lines here are now supposed to represent a piece of global ADS2. And there's the Rindler patch of ADS2. The black lines with arrows on them are the orbit of the time translation symmetry. And the blue curves are a regulated boundary. The dashed lines are the Rindler horizons. Now, to construct the solution we're interested in, we take two different spatial slices, the red line and the green line, which differ by some time translation by amount capital T, and we identify them. We identify the space by this time translation. And if we fill in the space in between, then we end up with a space that looks like this sort of double cone, where the compact direction on the cone, the circular direction, represents time. I drew the boundary there as wiggly to represent the boundary graviton degree of freedom in JT gravity. And indeed, the fluctuations of the SYK model about this connected saddle point correspond to the fluctuations of the boundary around this double cone. So this solution matches the correlated solution for the SYK model that we discussed before, but we can actually also just describe some properties of this independently. So first, the action is 0. The topological term that we discussed is 0 because this space has the topology of a cylinder, and the Euler characteristic is 0. The rest of the action vanishes because it cancels between the two sides of the cone. So this space here is the Jakiv-Teitelbaum gravity version of the SYK ramp. The zero mode factor of capital T arises in the same way it did before. We take the same cone, but we have to specify where the origin of time coordinates are on the two copies of the system. And a relative time translation of those two origins of time represent a physical zero. Okay, so the space looks a little bit funny though, and in particular near rho equals 0. So you could wonder whether this is well defined. And actually we're sort of still wondering that. we can zoom in on the fixed point of identification at rho equals 0 by looking at a Rindler space approximation to the cone, where this is the measure. Now, things can go badly here. So a naive regularization of this cone would be to replace the rho squared by rho squared plus epsilon squared, and this is singular as epsilon goes to 0. But even worse, because the space has this purely Lorentzian periodicity, the partition function, even of a free quantum field, would be ill-defined. However, the contour that we discussed in the microcanonical transform that defined the quantity y suggests a different kind of regularization of this double cone, where we replace rho by rho plus I epsilon. And this space is smooth. The curvature is 0. And although we don't know really whether quantum field theory, or more ambitiously string theory, can be defined on this space in general, and actually for reasons I might not have time to discuss, we hope the answer is no. Anyhow, at least in some cases, quantum field theory seems to be okay on this type of space. Okay, so far, really what we did was just translate this SYK solution into JT gravity variables. But this can be generalized. So you can consider a similar solution for any stationary black hole in any space-time dimension. You just take a thermofield double two-sided version of that black hole, the maximally extended version of the black hole, and you identify it by a killing time translation. So because the action is 0, black holes with all charges and all angular momenta will contribute equally. So we should sum over them, subject to the energy constraints. This actually seems reasonable because in a theory with global symmetry, in each symmetry sector, you'll have an independent set of energy eigenvalues. The full ramp of the theory will be a sum of ramps for each of those sectors. So there would be solutions in the supergravity theory dual to n equals 4 super-Young-Mills, and this leads to some puzzles in exactly how we're supposed to interpret these solutions. For example, in the case of n equals 4 super-Young-Mills, we expect an erratic ramp, like that extremely wiggly red curve from the beginning, not a smooth one that would be produced, at least naively, by this kind of saddle. Anyhow, okay, so let me summarize. In the SYK model, we can understand the ramp as arising from a non-trivial saddle point that correlates the two replicas that compute the spectral form. The saddle point can be translated to JT gravity, and it can be generalized to more general gravity. The interpretation of these things is not clear, and I hope to come back to this a little bit in the short talk on Friday. Thanks very much.
Thank you very much. There's time for questions. Any question upstairs?
Yeah, so you showed that numerics, which shows at the ramp part, the fluctuations start to be big.
Yes.
And how do I see that in this calculation? Does that mean you can do a similar calculation for multiple replica and see it's not self-average?
Yeah, so yes. For the disorder average, it's a smooth function, of course. You don't have any wiggles. But there's a way that you can sort of see that the wiggles were there by studying the disorder average not of z times z star, but of z times z star times z times z star. And if the curve were just actually a smooth curve with no wiggles in it, then that would approximately just be given by the square of the previous quantity. But in fact, what you find is that it's given by 2 times the square of the previous quantity. And that's because there can be additional saddle points where either of the z star factors are paired with either of the z factors. And you find a similar thing in the gravity solutions. So you could have, if we study 2k copies of this partition function, then there are k factorial ways of pairing them up. So it's sort of as though the gravity solutions know that they want to be describing something that is very wiggly, even though the naive answer actually is smooth.
So does that answer the question, the puzzle you mentioned about super-Young-Mills?
No, because we would like to get a wiggly function. Like if we're actually computing this in the bulk theory that's dual to n equals 4 super-Young-Mills, a specific quantum system, the answer should be an extremely erratic function. And the naive saddle point answer is a smooth function, so it's just wrong. It shares some aspects of the right answer, like the same time average and some of these higher statistics, but something about the calculation should be completely wrong.
Okay, here's one more question.
Sorry, Douglas. I might have misunderstood you, but did you say that in the JT model, you had to identify along the time, like the killing time, like
Yes.
direction
Yes.
by some period time t, right? And then why is that? And then this discussion, why is that okay to do given the geometry that, the t direction has that rho square, dt square? You had that discussion, but
Yeah, so this looks like a singularity, right? This is a
Yeah.
fixed point of the identification, and it looks like a singularity. And it could be that this is related to the problem with the wiggles, but I can't make a general statement, but in examples that we've looked at, the partition function of quantum fields on that space, regularized in this way with the rho plus I epsilon, is actually well behaved. So one way of sort of understanding why that could be the case is that with this regularization, with rho plus I epsilon, we can deform the rho contour into the upper half plane and just avoid rho equals 0 altogether. So we avoid that fixed point. Notice that that wouldn't have been possible for the second kind in red, where there's singularities at rho equals plus or minus I epsilon, and you can't form away from it.
Okay, the final question.
So for the slope in here, in various dimensions, you expect the power law to be different. If you use the decoupled geometries, do you get the different power laws? T cube is specific to SYK.
Yeah, that's right. So the answer for the slope that I gave was for SYK, this e to the 2s divided by t cubed. And that part is non-universal. That depends on the specific system that you're looking at. And indeed, that will depend on the type of, that depends on the space-time dimension of the black hole that you're considering. And actually, the calculation has not been done the calculation at this precision has not been done except in the two-dimensional case. But that part of the curve in many respects is less interesting because it's non-universal. It's the ramp and the plateau part that are more universal.
And can you elaborate a bit more why you think the relative time translation between the two copies is related to the ramp, the slope, the linear growth ramp itself?
Yeah, so there's two answers. One is that it gives a factor of capital T, and the ramp is proportional to T, so it matches the answer. There's another sort of answer, which is that there's an analog of this ramp factor. There's a way of understanding, sorry, the answer to this is a little bit too long for me to say it right now, but let me give a simplified version. There's a way of calculating the ramp in random matrix theory that involves where the factor of T comes precisely from a sum over cyclic permutations of some planar diagrams. And the sum over cyclic permutations is very much in the spirit of a relative time translation of the left and the right side. So in that sense, it sort of is a morally reasonable type of explanation, but more concretely, it just gives the right answer.
Okay, so I think we stop here. Thank you very much again, Douglas. And thank you. Also thanks to the other speakers. And as I was just told, the coffee break will go for half an hour, so we come back here at 4:10. Thank you.
please. We will start with Ksenia Bulycheva as our first speaker.
First of all, I'd like to thank the organizers for having me. Today, I want to talk about the SVK model with n equals to supersymmetry. First of all, why add supersymmetry to a perfectly sensible model? Well, it makes generalizations to higher dimensions much easier. So suppose we want to generalize to 2 dimensions. Then you'll need fields of conformal dimension 0 so that the random potential would be a relevant operator. And in 2 dimensions, a natural choice would be just take a scalar field. But with a scalar field, the random potential can have negative directions. And we want the potential to be bounded from below. By the way, it was supposed to say bounded from below, not positive definite. Anyways, if we instead just take superfields and instead of potential, take a random superpotential, then our potential energy will be non-negative and certainly bounded from below. And the last point is that if you take a specifically n equals 2 theory with a holomorphic and homogeneous superpotential, then it will flow to a true conformal point. Whereas an SVK model with a pure supersymmetry might have some boundary corrections which would drive it away from true conformal point. So I'll just flash briefly the calculation of the 4-point function and show you the tasted bit about. So we'll first of all we'll start with one-dimensional model. We'll work in a one-dimensional superspace. It's with supercoordinates tau theta and theta bar, even odd odd. We'll take chiral fermionic superfields, and together the chirality and SU11/1 group action allow us to make the cross ratio bosonic. And the 4-point function, which we are ultimately interested in, will be bosonic as well. So we can represent the 4-point function as a sum of ladder diagrams, or we can represent it as a symbolic sum like this. Here, angular brackets represent inner products, and Xi H are just eigenfunctions of the superconformal Casimir. And the fun thing is that these eigenfunctions are just simple linear combinations of the eigenfunctions of a non-supersymmetric SVK model, the usual SVK. So the sum here is over H, for which Xi H is normalizable. In particular, it means that H is either purely imaginary or integer, which means that this sum actually was an integral over imaginary axis. And the integrand will have a double pole at the origin, so we'll have to displace our contour to lie to the right of the origin so that we avoid this double pole. Having done so, we can rewrite the 4-point function as a sum of residues over the solutions of the condition k of h equals to 1, which of course describes the operator content of the model. In particular, the supercharge multiplet, supercharge operator, has conformal dimension 1, and not 0 as you might have expected for a conserved charge in a one-dimensional model. And of course, all this discussion is easily generalizable to 2 dimensions, because 2-dimensional superalgebra is just 2 copies of 1-dimensional superalgebra. You can also write the 4-point function as an integral. You'll also have to displace the integration contour away from the origin for the same reasons. Here, phi h is just a linear combination of Xi h, which we had in the previous slide. And from this 4-point function, you can also derive the central charge. And the central charge coincides with the central charge of usual n equals to s CFT, with the superpotential of degree q. Okay, I'm out of time, so you can also find the chaos exponent, and it will be less than 1, so its theory is not maximally chaotic. Thank you for your attention. That's all I wanted to say.
Is there a question for Ksenia? Okay, then we can move to the next speaker, Shai Chester.
My talk is on the M-theory S-matrix from 6C conformal field theory. So M-theory is a quantum theory of interacting supergravitons in 11 dimensions with no dimensionless coupling. A basic quantity of interest is the graviton S-matrix, which you can expand for small momentum, i.e. small 11D Planck length, which you write as L11. So here you see that on the right-hand side, you can expand it diagrammatically, where here I'm focusing on the tree-level terms, not the loops. And the first term is a vertex coming from the Einstein-Hilbert term, R. But then you also have other tree-level terms, which will come from covariant derivatives acting on R to the 4. And these are all the tree-level type terms you get in the diagrammatic expansion of the graviton S-matrix. So which of these terms are known? The lowest few terms are protected, and as a result, you can derive them from type 2A string theory plus duality. So in particular, these are their known values. But for all higher terms, they're not protected, and so there's no known way, even in principle, of deriving them, because we obviously don't have a world sheet because it's M-theory. So the goal of this talk is to tell you basically how you can, in principle, derive all the higher tree-level terms using ADS CFT. So M-theory contains two non-perturbative dynamical objects, M2 branes and M5 branes. And we in particular are going to focus on the 2,0 AN-1 60 SCFT that describes stacks of n M5 branes and is dual at large n to M3 and ADS7 cross S4. So this is the simplest 6C superconformal field theory. The quantity we're going to compute is a 4-point function of half BPS operators where k denotes the kth lowest dimension 1. We strip off these position factors just so that we can write it as a function of the usual conformal cross ratios. And then according to ADS-CFT, this quantity gk is dual to a correlator of the kth lowest kk modes of M3 and ADS7 cross S4. Finally, one can take the flat space limit of this 4-point function to recover the 11D S matrix restricted to 7 dimensions, with the momentum restricted to 7 dimensions, which we denote by A with a subscript 7. So we're going to compute this by going to Mellon space. So in particular, we're going to consider the Mellon transform, which we denote as MK, which is now a function of ST and U, which are like Mandelstam variables in this Mellon space. So it's kind of like a Fourier transform in a sense. In a large N expansion, we can choose to write this Mellon transform of the tree level terms as in terms of these terms MKP, where P denotes the degree of the Mellon amplitude when ST and U are large. Then we can actually fix these MKPs using 3 principles: crossing symmetry, the superconformal Ward identity, and lastly, the fact that poles in terms of these ST and U variables correspond to dimensions of operators in the OPE we're interested in. And in particular, if we want to focus on tree level, so ignoring loops, then we only allow poles for half BPS operators. Finally, after deriving what these MKP are, we can take the flat space limit, and that tells us that a Mellon amplitude which has 2 P derivatives, a Mellon amplitude of degree P contributes a term with 2 P derivatives in the flat space S matrix. So for instance, a degree 1 Mellon amplitude would correspond to a 2 derivative term in the flat space S matrix, i.e. the Einstein-Hilbert term. So using these 3 principles, we can basically bootstrap this Mellon amplitude. So this was done for the degree 1 Mellon amplitude by these gentlemen. They got one solution, and then you can fix its coefficient in terms of the central charge. It's proportional to n to the -3, and this is as expected. What we did is we looked at higher degree Mellon amplitudes. So for instance, for degree 2 and degree 3, there aren't any, which corresponds to the fact that in the flat space S matrix, there is no R squared or R cubed terms. More interestingly, for P between 4 and 10, we were able to write the flat space S matrix in terms of a small set of CFT6 data. We can't go beyond p equals 10 because then the large n scaling of these terms is the same as the loop terms, and so the tree level expansion is no longer well defined. In particular, our most interesting result is that the degree 4 term is fixed by a half PPSOP coefficient, which can be computed exactly. And then using that, when we take the flat space limit, we're able to correctly reproduce the known R to the 4 term in the flat space S matrix. Thank you. So.
We can take a quick question if there's any. Or we can move to the next speaker, which is Yogesh Dandekar.
Hello. I would like to thank the organizers for this opportunity. So my talk today is based on the paper that we did with my advisor Shiraz Minola and some students. So firstly, I want to review what is the large D membrane paradigm, the relevant progress for my talk. So the main point is that the dynamics of black holes reduces to the dynamics of membrane in large spacetime dimension. The membrane is a co-dimension one time-like non-gravitational surface which is embedded in unperturbed background spacetime, for example, flat. So the membrane variables are its arbitrary shape and the velocity field, which I denote by U. They are d-1 in d spacetime dimensions. So the membrane equations of motion are obtained in a perturbation series in 1 over t. And membrane hosts a stress tensor and entropy current on its world volume of this form. So P is the projector, sigma is the shear. This is the Brown-York tensor part. The dots represent the subleading corrections. Entropy current just U by 4 plus subleading corrections. So space-time stress tensor conservation actually gives you D equations, out of which d-1 come from the world volume conservation of this membrane stress tensor. And one equation comes from the identity k mu t mu is equal to 0. But it is obeyed identically order by order in 1 over d. So this tells you that the formulation is strictly consistent only at large d. Then the number of equations become the number of variables. Notice that it also obeys local form of second law at large d. So now the topic of today's talk is improved arbitrary D membrane. So I construct the stress tensor and entropy current of this form, where W is defined like this. So notice that it is just sum of a Brown-York part and a fluid kind of part. I consider this improved membrane in any background that solves the Einstein equation. Notice that it obeys this identity exactly, even at arbitrary D. So this tells you that the formulation is consistent for arbitrary D as we saw. And notice that it exactly obeys the local form of second law. It reduces to previous stress tensors and entropy current at leading order in large D. So we are guaranteed to reproduce black hole physics at least at large D. So it is like a finite D, it is a like consistent finite D completion of the leading large D membrane equations. Notice in particular that the energy density for this stress tensor vanishes. Pressure and temperature depend on this quantity W, and in particular eta over S is 1 over 4 pi. So I now consider the stationary solutions of this improved membrane. So in stationary case, velocity is proportional to Killing vector. And so the conservation of the membrane stress tensor gives you this simple shape equation where T naught is an arbitrary constant. Now I consider the action of this form where M is the membrane world volume and V is the space-time which is enclosed by this membrane world volume. So I consider infinitesimal changes in shape, and imposing the condition that the variation of this action vanishes, I recover the shape equation. I also recover the stationary stress tensor by taking the variation of this action with respect to the induced metric. Notice that the action on shell reduces to just energy by T naught minus entropy if I identify this arbitrary constant T naught with the temperature of the stationary solution, which is just minus log of thermal partition function. Notice that it obeys del beta S is equal to E on shell as expected. So now I want to describe some surprises at finite D. So the thermodynamic quantities of static spherical membrane in ADS flat or DS background they match exactly at finite d, which is surprising, with the dual Schwarzschild black hole. Now consider another situation in which I consider slowly varying planar membrane in ADS, calculate its linearized gravitational field source by it, and I calculate the boundary stress center in terms of the boundary variables, which is of this form. Notice that it matches exactly at finite d with the fluid gravity stress sensor up to first order in derivative expansion, which is surprising. As expected, it agrees with fluid gravity at second and higher order in the large D limit. So let me summarize. So it is a special kind of membrane dynamics which is well defined at arbitrary D. We derive simple shape equation and action for stationary case. Action on shell reduces to thermal partition function. Reproduces black hole physics better than expected for finite D. Now some open questions. Can simulations of this improved membrane capture key features of black hole dynamics? Can we construct a membrane formulation such that it can reproduce all the stationary black hole solutions exactly at finite D? Also, can we understand dynamical second law of black hole thermodynamics for higher derivative theories of gravity? Thank you.
Next speaker is Masazumi Honda.
I'm Masazumi from Weizmann Institute. I will talk about my paper in last year, which will be published in PRL. Original title of this paper was Role of Complexified Supersymmetric Solutions, but it was changed by PRL to Supersymmetric Solutions and Borel Singularities for n equal to supersymmetric Chern-Simons theories. Let me start with a question behind this talk. It is not usually mentioned, but in supersymmetric field theories, there exist configurations which formally satisfy supersymmetric conditions, but are not on original path integral contour. Let us call this type of configurations by complexified supersymmetric solution. Now I'd like to ask what are physical roles of complexified supersymmetric solution. Here, I'd like to I propose part of answers for these questions. I propose complexified supersymmetric solutions provide important information on large order behavior of perturbative series in supersymmetric theories. Before going to detail of this proposal, I have to introduce a mathematical tool called Borel summation, which is one of the standard techniques to resum non-convergent series. Given a perturbative series, Borel transformation is defined in this way. This is roughly given by division by factorial at each order. Then, Borel summation is defined as a Laplace transformation of Borel transformation. And especially here, singularities of Borel transformation is very important because their locations determine whether or not perturbative series are Borel summable, and how perturbative coefficients grow at the large order. Now I am ready to make a precise conjecture. Actually, I have found two types of complexified supersymmetric solutions. One is bosonic solution, and the other is fermionic solution. And the basic idea is bosonic solution corresponds to pole of a Borel transformation, while fermionic one corresponds to zero of a Borel transformation. Here is a conjecture. I propose if there are NB bosonic solutions and NF fermionic solutions with action Fc over G, then I propose Borel transformation include this factor. Namely, Borel transformation has a singularity at the T equal Sc when we have a more bosonic solutions. And in my poster, we will explicitly check this conjecture for supersymmetric observables in three-dimensional n-equal to supersymmetric Chang-Simons matter theory. More concretely, I will construct infinitely many complexified supersymmetric solutions in general 3D n-equal to supersymmetric theory on sphere with Lagrangian. Then I will compare their actions with the Borel singularities for 1 over k expansion, or equivalently, perturbative expansion by inverse of Chang-Simons levels. And there are also related progress, not in poster, such as a connection to resurgence, supersymmetric breaking, or effective theory. That's it. Thanks.
Questions? In that case, we can move to the next speaker, which is Chang-Tse Hsieh.
Okay. I'm Chang-Tse Hsieh. I'm a joint postdoc at IPMU and the Institute for Solid-State Physics. In this Gong Show presentation, I will briefly introduce my work about the modern perspective of discrete gauge anomalies, which will appear soon. I would also like to thank useful discussions with my PhD advisor, Shinsei Liu at the University of Chicago, Edward Witten at IAS, Yuji Tachikawa, Katsuya Yonekura, and Hiroshi Muraya at IPMU. Cancellation of gauge anomalies is a fundamental constraint on a consistent quantum field theory. For example, a U1 chiral gauge theory is anomalous when coupled to gravity if the cancellation condition involving both the periodic gauge and the mixed anomalies is not satisfied. While anomalies of continuous symmetries are well understood, how about the case of gauge anomalies associated with discrete symmetries? In this case, there are only global anomalies, and one cannot use a usual method, such as the perturbative Feynman diagram technique, to calculate them. In the paper by Kravchuk and Welcher in 1989, they also mentioned identification of such anomalies as difficult but well-developed art, in which I will show and here. A difficult but well-developed art. This quite motivated me to study this problem. For example, you might be interested, how do we couple wild fermions consistently to a topological ZN gauge theory in 4D? In some cases, we might be able to write down such a theory as the following local action. There are two kinds of ZN chiral gauge theories, depending on the symmetries of fermions, which can be described by either an untwisted or a twisted symmetry group incorporating the spin and the gauge groups. Of course, there have been several attempts to tackle this problem. Let me review some of them. Ibanez and Rose in 1991 argued that the untwisted ZN anomaly constraint can be deduced by the anomaly cancellation condition of a UV embedding chiral gauge series plus charge constraint on massive states through spontaneous symmetry breaking of U1. Consequently, they obtain a necessary condition of another free ZN charges, including both the cubic and the linear constraint, similar to the case of U1 symmetry. Soon after this work, Banks and Dye made some comments on it. They indicate that only the linear constraint should be satisfied, while the nonlinear constraint might be too restrictive and might not be required for consistency of the long energy theory. The work by Saki and Murayama in 1997 addressed a similar conclusion. Two types of discrete anomalies are involved by anomaly matching argument. Type 1 anomalies, the matching conditions have to be always satisfied regardless of the details of the massive bounded state, while the type anomalies have to be also matched, except there are fractionally charged massive bounded states in the theory. Okay, so here I revisit this problem from a more modern perspective based on concept of symmetry protect topological faces from a condensed matter physics and also from a refined definition of global anomalies by Witten recently. So it's based on geometric and topological considerations. To be more precise, we compare the anomaly of a Zn global symmetry deduced by the consistency of formulating the theory on a generic manifold with either untwisted or twisted spin structure and a background Zn gauge field. And this is my main result. Maybe I will skip, but there are either the untwisted case and the twist case. And I want to point out in all these equations, only the cube and linear term are present as expected. So we propose a reformulation of evaluated discrete gauge anomalies of an underlying chiral gauge theory. While agree with previous works by annihilation argument, our result provides, from a purely low energy perspective, a more complete aspect of discrete symmetry anomaly. Respect this work. Thank you.
The next speaker is Patrick Jefferson.
Thank you very much, and also a very big thank you to the organizers of this conference. So the subject of my talk today is going to be SCFTs and the relationship with supergravity, and in particular, I'm going to discuss how to use this relationship and to use what is known about 6D and 5D SCFTs to better understand some aspects of 6D and 5-dimensional supergravity. And the key insight here is the observation that since 6D and 5D theories in general, both SCFTs and supergravities can be engineered by compactifying F and M theory on singular Calabi-Yau threefolds, the relationship between SCFTs and supergravity can in principle be understood as a relationship between non-compact Calabi-Yau threefolds and compact Calabi-Yau threefolds. So what do I mean by this in particular? Let me discuss a couple of examples. First example is 6D SCFTs. And 6D 1,0 SCFTs are associated to singular Calabi-Yau threefolds, which are non-compact. And in general, these can be understood as the dynamics of 7 branes wrapping P1s in the base of an elliptic fibration. The full Calabi-Yau threefold is an elliptically fibered threefold over some base, which I'll call B. And this configuration of P1s in the base can shrink. And the shrinking, the vanishing of this configuration of curves is associated to the SCFT fixed point. So in particular, I like to focus on a particular class of SCFTs called G, G prime conformal matter theories. And these theories are characterized by the existence of a global symmetry subgroup G cross G prime. And these theories are important to my discussion because they have an orbifold realization in terms of non-compact threefolds, namely T2, just a 2 torus times C2 mod the abelian group Zm times Zn. So here I give a schematic picture. You can think of these two curves G, which are labeled by G and G prime as non-compact curves in the base, and then this point of intersection, which I represent by a black dot, is a configuration of P1s represented by this graph, and they intersect transversely, and these labels N1 through Nk represent the self-intersection, minus the self-intersection of these curves in the normal geometry. So what's the relationship to compact threefolds? Well, if you consider a class of compact Calabi-Yau threefolds, T6 mod Zm times Zn, these contain the G, G prime conformal matter theories as local singularities. However, the compactness of the threefold means the symmetries G and G prime, which were global symmetries originally, are gauged. So example, T6 mod Z2 times Z2 contains 16 copies of D4 conformal matter. And the non-compact curves, which are initially so if you were to zoom in and focus on one of the SCFTs, these look like non-compact curves carrying some global D4 symmetry, And in this case, because of the compactness of the threefold, these are now gauged. So here you see 16 -1 curves, and then these are connected by an additional 8 -4 curves. So these -4 curves initially would have been the non-compact curves, but they're compactified in the base of this threefold. So this gives us a prescription for gauging these global symmetries. Another example, which I'll just discuss very quickly, is 5D theories. 5D SCFTs are associated to non-elliptic threefolds, and an example of these would be toric threefolds. And so here I've just given a schematic description of the 5D T5 theory. This is the PQ 5-brane web in type 2B. And notice that this theory has SU5 cube global symmetry. It's represented by these collections of parallel lines. So these toric singularities naturally appear inside of a compact threefold, a family of compact threefolds as well, and these are mirrors of hypersurface threefolds. And the example that I have in mind that I'd like to discuss here very briefly in the few seconds that I have left is just, excuse me, the mirror quintic, where you can see there's a collection of these singularities appearing, and their global symmetries are now gauged, and you can think of the gauging as some trivalent SU5 vertex. So what can we learn from this picture? Well, there's three things in particular. One thing is we can find an example of a theory, effective theory that we can use to describe the holographic dual of ADS3 cross S3 times T4 mod Z2. That's the 6D example. And in the 5D family theories, we can use this toric picture to generalize the topological string partition function and potentially compute topological string amplitudes for the full compact mirror quintic. So I'll stop here. Thank you very much for your time.
The next speaker is Sitender Kashyap.
Good evening, everyone. Today I'm going to speak on equivalence of amplitudes involving massive string states in pure spinor and RNS formulation. And this talk is based on these papers, along with my collaborators Shubhranil and Mrityunjay Verma. We are thankful to Ashok Sen for numerous useful discussions. So let's get going. Let me thank the organizers for this opportunity. Now we shall present our results in three parts. The part one is essentially theta expansion of unintegrated vertex operator. Part two is the construction of integrated vertex operator, both of these at mass squared equal to 1 over alpha prime. Finally, the third part involves computing some tree level amplitudes. And the point is, for consistency, these amplitudes must agree with RNS formulation results. What we find is that they do, and for this talk, we will work with open strings. So let me describe the unintegrated vertex operator as first excited level of open string. They form, the states at this level form an unequal to 1 spin 2 supermultiplet, which comprises a tensor spinor field containing 128 degrees of freedom, a symmetric traceless tensor containing 44 degrees of freedom, and three-form field BMNP comprising of 84 bosonic degrees of freedom. And all of these are taken to be theta independent component of the corresponding capital lettered superfield psi, g, and this thing. And the way these superfields appear in the unintegrated vertex operator was given by these people. For instance, this B alpha beta is expressed in terms of BM and P, and so on and so forth. For example, this C is in terms of C, but this is again here, and this H is psi. So this is the point is that all these things go into the unintegrated vertex operator. Next, the point of this exercise is that theta expansion are a must for computing scattering amplitudes in pure spinor, and the theta expansion is done by making use of these equations, which relate lower order components to higher order components here. And after doing this exercise of recursive relation, what we find is, for instance, the tensor spinor superfield has this theta expansion till order theta cubed. And similar results for BMNP and GMN. Now, as you can see, there are a lot of terms, so which it becomes very difficult to handle. For this, one can resort to computer algebra systems. Our choice was Cadabra and a Mathematica package called Gamma. So with this, let's go to integrated vertex. I'll just give the form. It is given by this, comprising of 10 terms, and these this is actually in terms of all the 3 superfields that I mentioned. And as you can see, the way we solve for this is using this equation, which relates the integrated vertex operator to the unintegrated vertex operator through this PRC charge and the worldsheet derivative. So the point is, given V, solve for U. And we did that. And the result was in the previous transparency. Now, the point is of these 2 exercises, the construction of integrated vertex operator and the theta expansion is that they provide us important lessons which can be used to generalize the to get the states at all mass levels, both in integrated and unintegrated form. For details, please have a look at my poster and Mrityunjay Verma's. Finally, we compute some scattering amplitude, tree level, and these are given by this correlator, where we are the unintegrated operators, you are the integrated ones. As it so happens in pure spinner, all non-zero amplitudes must have 3 lambda 0 component, the pure spinner, and 5 theta 0 modes. And all these non-zero correlators will be normalized by this correlator. With this, we compute certain amplitudes involving 2 massless and 1 massive fields. At massless level, we have n equal to 1 super Young-Mills, which has gluon, gluino, and at massive level, these are B, B, G, and psi, which I described. Here, E's are the polarizations, and K's are the momenta. So now, the result is this. There are 2 points. One is a tensor structure, and then there are some amplitudes in which there are more than 1 term. And the important thing is relative factors. So this amplitude is in pure spinner. And what we find that on doing the analogous computation in RNS is that this pass both tests. Except, I mean, we have to yet figure out the overall normalization, which we will do in the forthcoming publication. Thank you.
The next speaker is Petr Kravchuk.
Okay. All right, let me first thank the organizers for putting together this wonderful conference. I will tell you about this paper that we published last May with David Simmons-Deffen. And to start with some motivation, let us consider a 4-point function of scalar operators in conformal field theory. So you can think about, for example, three-dimensionalizing CFT. It doesn't have to be weakly coupled or two-dimensional. And consider the conformal partial wave expansion for this 4-point function, which has the form of sum over integer spin j, an integral over scaling dimension of some function c delta j against the conformal block. The function c delta j has a property that is a meromorphic function in delta with poles at scaling dimensions of the physical operators and residues proportional to products of operator product expansion coefficients, so that by deformation of the contour delta, you can pick up these poles and recover the usual conformal block decomposition of the point function. So last year, Simon Kern-Hood derived a very interesting inversion formula for this expansion, which expresses c delta j as an integral of a particular double commutator against the conformal block. And notice that this conformal block has a funny feature that has scaling dimension and spin swapped compared to the usual block. The most interesting feature of this formula is that it defines an analytic continuation of c delta j and spin j, and therefore also these quantities which enter in this definition. And also let me mention that we know already that non-integer values of j are physically important because, for example, they give you the behavior of the 4-point function in rigid limit. Given this information, it seems natural to ask some questions, and the main question is whether we can leave this analytic continuation to operator level. In other words, whether we can have analytic families of operators parameterized by spin, which at integer spin reduced to usual local operators. Before we can answer this question, we also need to understand whether continuous spin operators do even make sense in conformal field theory. And also in the paper we study other questions related to generalization of Lorentzian inversion formula, which I showed in the previous slide, and conformal J theory, and the average null energy condition, which
I will not have time to discuss these questions in detail, but I will show some formulas in the last slide. So to start answering these questions, first of all, yes, we can consider continuous spin operators in conformal field theory, and we can think of them as just being functions of coordinate and an optimization vector, which transform under conformal transformations in a natural way. And the spin is encoded in homogeneity property of this function with respect to z. Given this definition, one can prove a simple lemma that in a theory with positive energies, we necessarily have that any non-integer spin operator annihilates the vector state. This makes it problematic to analytically continue local operators in spin because you have local operator not annihilate the vacuum state, and therefore you cannot have an analytic function of J, which reduces to local operators in integer spin. To get around this complication, we instead analytically continue so-called light transforms of local operators, which do annihilate the vacuum. And light transform is a conformally invariant integral transform, which you can apply to a primary operator O, dimension delta and spin J, to obtain a primary operator with dimension 1 minus J and spin 1 minus delta. This swap in dimension ends up explaining the appearance of finite conformal bulk in the inverted form. A familiar example of light transform is the light transform of stress tensor, which is just the average alignment operator. To define the analytic continuation, we construct an informally invariant kernel K delta J, which is analytic in delta and J, and we define the analytically continued operators as residues of this expression in delta. In free theories, we can explicitly compute this, and we obtain expressions which coincide with well-known expressions for continuous spin operators in free theories. So this explains how we can analytically continue operators in spin, and here are some formulas that we can show you, which describe some generalization of Lorentz inversion formula and some natural expressions for the residual limit of the 4-point function. The point of these formulas is that I don't have time to unpack the notation, but the idea is that everything has a natural expression in terms of conformal invariant operations, and in particular involving light transform. Thank you.
The next speaker is Craig Lawrie.
Okay, it is my pleasure to be here and to be able to report on some recent work that my collaborators and I have been doing, specifically on this paper here, which came out last week. So my collaborators are Dario Mortelli and Sakura Sheffer. Okay, so first let me begin just by reminding you of something which I'm sure many people in this room know a lot about, which is that there is a class of 4D n equals 2 field theories called class S theories, which were written down a construction in 2009 by Gayoto. So specifically, these theories begin by taking the 6D theory on the world volume of the M5 brane, and then putting it on a product manifold, where one of the factors in the product is an n-punctured genus G Riemann surface. Okay, then the 4D theory in the low energy limit is the class S theory. And what is the relevance of the curve for this theory? Well, as is now well established, the complex structure moduli of that curve are related to the gauge couplings in the resulting 4D theory. So we ask ourselves the question, how may we generalize this construction? And one thing which comes to mind is that what if we relax the assumption that the world volume of the M5 brane is a product? So for example, what if we consider the world volume to instead be a non-trivial fibration where the fiber is an n-punctured genus G Riemann surface? In this case, one still gets a 4D theory, but now what is it? So the gauge couplings were related to the complex structure moduli, but in a fibration, the complex structure moduli now vary over the 4D space. So that means we have space-time varying coupling. Similarly, the fibration has singular fibers, and these singular fibers have monodromy in the duality group of the theory. And these are defects, codimension 2 defects, which are sometimes known as duality defects. Okay. So I've given sort of a very quick description of a certain class of 4D theories, but can we learn anything about these theories? One thing that we can still learn about them, even though they're these complicated, strongly coupled theories with defects, is their anomalies. So we understand the anomaly of the 6D 2,0 superconformal field theory living on the M5 branes. It's gravitational and R symmetry anomalies. And we know that if we start with a higher dimensional theory, we can work out the anomalies of the lower dimensional theory by integrating over the anomaly polynomial over the compactification space. In this language, this means that we must take the I8, which is defined on the 6D spacetime, and push it forward to some form I6 defined on the 4D spacetime. This will tell us part of the anomalies of this theory. So the simplest example is where we take the fiber to be a torus without punctures, and the result of the push forward is written here. Okay, so just a few things to highlight here is that this involves some particular line bundle, and this line bundle is related to exactly how the complex structure moduli of the torus varies over 4D spacetime. So it has a connection which looks something like this. One can see that all the terms that I've written in color here, these are new terms, and these vanish in the class F limit, which is where we take the fibration just to be a trivial product. Okay, so that was kind of a definition from 6D, but I would like to give an intrinsic four-dimensional description of these theories. And for the C equals T2 case, we can indeed do that. So this theory is n equals 4 super Young mills with duality defects. And in such a background where you turn on the duality defects, there is an additional U1 symmetry under which the fermions are charged, comes coupled with the SL2Z, and this also gives rise to an anomaly. And this can be worked out by standard methods and looks like this. Notice that these two anomalies are different, and the reason for this is that we only use the gauginos here, so the defects are not included. In fact, we can look at the difference to determine the contribution from the defects. Okay, and it looks like this. This is at least the universal part of the contribution from the defects. That means that it's true for any possible choice of consistent network of duality defects. Okay, and we cross-check this by looking at further compactifications of these 4D theories down to 2D. And there it's related to strings in 6D, or else holographic constructions with varying axial dilaton. Okay, so I'm out of time, but if your appetite has been whetted in this short period of time, I invite you to come and look at my poster outside, and I will stop there. Thank you.
The next speaker is Alexandru Lupsasca.
So who's next? Hello. Today I'd like to tell you about a project that I've been working on with Andy Strominger and 3 graduate students, which would come out very soon, in which we use ideas and tools from high-energy theory, particular conformal symmetry, to make a prediction for an ongoing experiment at the observational frontier in astronomy. Okay, so in general, this is a thrilling time to study black hole physics, which has finally become an experimental science following LIGO's historic discovery. And another experiment, the Event Horizon Telescope, now promises to soon deliver the first up-close pictures of real black holes in the sky. And this poses an immediate challenge to theorists who must answer, what will the image look like? And it turns out that this is very difficult to predict because, well, essentially astrophysics is hard. Black holes, even though we know their space-time geometry, are also surrounded by an accretion disk and a plasma magnetosphere, and may also have a corona, jets, and so on. And so each of these ingredients obeys messy physics, which means that the traditional approach has been to run computer simulations. But detailed simulations are time-consuming and costly, and moreover, they can be incomplete or altogether fail in a special corner of parameter space, that of high-spin black holes. So by high-spin black hole, I mean one which saturates this curve bound that says that the spin of a black hole cannot exceed its mass squared. When a black hole saturates the bound, it's extremal, and the space-time geometry near the event horizon develops an infinitely deep throat. And so in this regime, numerical studies are confronted with the separation of scales, because resolving the near-horizon physics requires a large grid with an increasingly fine resolution. But in physics, analytics and numerics are often complementary, and whenever you have a large separation of scales, there's a small parameter, and you can hope to do perturbation expansion in that parameter. And here, the small parameter is the Hawking temperature, which vanishes at extremality. So you can define perturbation theory around a very special point, which is the zero temperature black hole. And that is a special point because the region near the event horizon of such a black hole has local scale invariance or conformal symmetry. And intuitively, that's because the throat becomes infinitely deep, and it looks like ADS. So this observation that you can do a temperature expansion around a point with conformal symmetry suggests that physics near rapidly spinning black holes should be constrained by conformal symmetry in much the same way as many near-critical condensed matter systems are governed by conformal field theories. And in this project, we use the conformal symmetry to analytically compute the polarization profile of near-horizon emissions from a high-spin black hole. This result is directly relevant to ongoing observations of the Event Horizon Telescope of the black hole at the center of M87. And that's because our prediction relies only on three assumptions. One, that the black hole is rapidly spinning, and M87 is known to be above 98% of extremality. Two, that the Event Horizon Telescope can observe near-horizon emissions, and they hope to get 20 pixels across the horizon. And three, that the polarization profile of the source is invariant under the enhanced isometries of the near-horizon geometry. And that's a natural assumption to make in astrophysics. For instance, accretion disks of black holes tend to be stationary and axisymmetric because the Kerr metric is stationary and axisymmetric. So here we're in the throat of the black hole, which has additional symmetries, and we assume that the source polarization respects them. Now, because the polarization must also obey other equations like parallel transport along geodesics, this is a highly over-constrained problem, but surprisingly, a solution nonetheless exists, and moreover, it is unique. So instead of showing you the formulas, I'm just going to plot some polarimetric images. The one thing you need to know is that a black hole, when it is backlit, like any object, will cast a shadow, but because gravity bends light, the shadow can be really quite funny, and so you get some wacky results. And I'm going to show you very briefly three cases, which are very different, and if you want to see more selfies, you can look at my poster. So this is the example of a black hole that we're looking at from above, right on the axis of rotation. And the red circle in the middle is the apparent size of the event horizon. It's what the black hole would look like if there were no gravity, but instead you get this much larger shadow, which is filled by light from the throat. And you get this pattern of polarization whorls, which end and begin at apparent locations of the poles. So the center is the North Pole, and then the concentric circles are different images of the poles, and the entire surface of the event horizon is unfolded infinitely many times over in this image. So you would see something like this. Now, if you look at the black hole from the side, it's even wackier. You can see both the North Pole and the South Pole simultaneously because of light bending, and moreover, the shadow develops this vertical edge, which is very special, has a lot of structure, and for instance, we've shown that if you had an accretion disk around the black hole, all the emissions from the accretion disk would end up on this line with a very particular pattern, which is controlled by symmetry. There's a hypergeometric function there. And so you would see something like this. Now, finally, for M87, which we're looking at from about 15 degrees off axis, this is what you'd expect to see. So this is not a numerical simulation. It's a plot of an analytic formula. And you can see, again, a polarization whorl around the North Pole and the South. Thank you.
The next speaker is Thomas Mertens.
Okay, I'm going to talk about the Schwarzschild and black hole physics, which is based on these papers. So the theory that I want to study is the Schwarzschild theory, for which the Lagrangian is the Schwarzschild derivative, which is written here. And this theory appears in at least two circumstances. One is the SYK model at low energies, where the Schwarzschild theory describes the regime of n goes to infinity and strong coupling. The second situation, which turned out to be related to the first one, is the Jacques-Yves-Teitelbaum 2D dilaton gravity model, where Jacques-Yves-Teitelbaum is holographically dual to the Schwarzschild theory, and the dynamics of the wiggly boundary curve at the boundary of the Jacques-Yves-Teitelbaum model is described by a Schwarzschild derivative action. And you should compare this to the Chern-Simons WCW or 3D gravity Liouville topological kind of dualities. So the main goal of my talk is to compute all correlation functions of this theory. So I take this Schwarzschild derivative action here and I put it in this path integral. I'm path integrating over all time reparameterizations of the thermal circle. So my integration space is diff S1 mod SL2R. And the operator insertions that I have, well, it turns out that the most natural ones are bilocal operators, so they depend on two times. and they are of this form. So f dot tau 1, f dot tau 2 divided by sine squared of f tau 1 minus f tau 2 to some power L. So I insert this expression in here, and I want to compute this path integral. I have introduced this big C coupling constant, and if I take that limit that big C goes to infinity, I'm probing the semi-classical regime, where I expect to find semi-classical gravitational bulk physics in my exact correlators, and that's what I want to study. So the method we used is 2D Liouville CFT. So consider 2D Liouville on a cylindrical surface between these Z-branes, so as the left figure here. And now I take a double scaling limit that I will call the Schwarzschild limit, where I simultaneously send the 2D central charge to go to infinity, and I take the radius of the cylinders to go to 0, keeping their product fixed and proportional to big C, which will turn out to be the Schwarzschild coupling constant. Now, you can prove using path integral techniques that 2D Liouville theory in this particular setup really reduces to the Schwarzschild theory, and you, as a bonus, you get a dictionary on which Liouville objects map to which Schwarzschild objects. In particular, the Liouville stress tensor maps to the Schwarzschild derivative itself, and a Liouville primary vertex operator maps to the Schwarzschild bilocal operator that I mentioned on the previous slide. So we are led to consider Liouville amplitudes between these Z-branes on a cylindrical surface with these Liouville primaries in between, and take this double scaling limit, and that should compute for us Schwarzschild bilocal correlators. So what are the results? Well, the simplest case is a two-point function, which is just one Schwarzschild bilocal operator. I can diagrammatically draw this like this. And the answer turns out to be this expression, which has two integrals, 1 over k1, 1 over k2, each with this typical Sinh measure that appears all over in this Schwarzschild theory. Then some Hamiltonian propagation factors and some vertex functions. So while this expression looks complicated, it has a nice interpretation in the semi-classical regime, so where I take this big C to go to infinity. Because in this regime, you can see quasi-normal modes, and you can see the Jacques-Teitelbaum black hole mass as a function of Hawking temperature. So you can interpret this expression as a black hole that emits and reabsorbs an excitation. And you can generalize this to higher point functions, but the most interesting one is the out-of-time order 4-point correlator. So I can draw this in this diagram like this. And if you use the same techniques as before, this is the expression you find. So structurally, it looks similar, a bit more complicated, but the same structures appear. The only difference, or the only new ingredient, is this 6J symbol of SL2R that appears here. And that represents the crossing of the lines, so putting the operators out of time order. And this descends from the braiding R matrix into the Liouville CFT. So as an application of this, you can study the semi-classical regime of this complicated expression. And if you do the computation, in the end, you end up with this expression, where Q plus and P minus are Kruskal momenta. This psi and phi are Kruskal wave functions, or bulk to boundary propagators, and this is dressed with this Dreit-Hove-Chock-wave S matrix. And this is, of course, precisely what you would expect when you would semi-classically write down the expression for the out-of-time relation. And then finally, as an alternative perspective on this entire story, you can also compute these Schwarzschild correlation functions without resorting to the Liouville CFT by giving a bulk perspective to this entire story. And in particular, you can view the Schwarzschild bilocal operators as boundary-anchored Wilson lines in an SL2R BF theory, as I've drawn here. That's why they're bilocal. And you can also see, or you can compute that when these Wilson lines cross, then you need to write down a 6J symbol of the group here, and that's why 6J symbols of SL2R appear to me. Okay, so thank you.
The next speaker is Emily Nardoni.
Okay, thank you very much to the organizers for giving me the opportunity to speak here. The arena for this talk are the 6D2,0 SCFTs of type AN-1, which are the effective world volume theories of N-stacked M5 branes. And we take these topologically twisted over a Riemann surface of genus G with N punctures. The topological twist is needed to preserve supersymmetry in the IR. And the resulting 4D SCFTs that we get out of this procedure are known as the theories of class S. These were also introduced by Craig a little bit earlier. The 4D SCFTs are labeled by the data of the Riemann surface, including the Euler characteristic of the surface and local data at the punctures. The punctures are boundary components, and boundary conditions are needed for the branes. This leads to flavor symmetries in 4 dimensions, which in this setup are one-to-one with Young tableau. The main point I'd like to emphasize here is that this setup allows us to organize a large space of generically strongly coupled QFTs geometrically, where much of the richness of this space comes from the choice of punctures on the Riemann surface. So our goal was a first principles way of computing Tuft anomalies when compactifying M5 branes on a Riemann surface for both the n=1 and n=2 cases in 4 dimensions, but for simplicity here I'll restrict to n=2. In general, one can reduce anomalies to lower dimensions. This will capture the contribution of the lower dimensional anomalies due to the compactification. For class S, when there are no punctures on the Riemann surface, this method has been really powerful in computing the anomalies of the 4D theories. But with punctures, there are additional contributions to the anomalies due to new degrees of freedom at the punctures. These are known indirectly by what one might call a bottom-up approach from various QFT dualities and Higgsing arguments. And so what our work did was show how to modify this prescription to compute these directly. The method we used was anomaly inflow for the M5 branes. In the presence of an M5 brane, bulk diffeomorphisms localized on the brane are anomalous. The anomalies are canceled by terms in the bulk 11D supergravity effective action. This integrand is related to the 8-form anomaly polynomial of the 6D theory via the descent procedure. So here's the roadmap for inflow for M5 branes in these class S geometries. The M5 branes magnetically source the 4-form M-theory G4 flux. The right-hand side of this Bianchi identity must be smoothed to a bump form wedge, the gauge invariant closed globally well-defined angular form on the normal SO5 bundle to the branes. Then generalizing to class S geometries and implementing the twist, the normal bundle reduces to reflect the n=2 R symmetry that's preserved in 4 dimensions. This right-hand side is a function of connection forms for background field strengths over the 4D base and the Riemann surface. In particular, the connection form over the Riemann surface picks up sources at the locations of the punctures. Then the variation of the effective action gets new contributions from boundary terms in the integration by parts. The form of the sources is motivated by the holographic description. So this curvature form over the Riemann surface gets sources that are localized on the Riemann surface and along a transverse direction to the branes. This is this mu direction. Each source is a KK monopole in M theory, and some of the original N M5 branes can end on it. The symmetries of the sources induce global symmetries in the 4D theory. And then sources for this connection form on the Riemann surface imply sources for G4, which must be smoothed. So then in the variation of the action, there are 2 types of terms that contribute. The first localizes on the branes, and this gives the normal 62,0 8-form anomaly polynomial, except now the integrand depends on the full improved connection forms, and then reducing over the Riemann surface gives the known answer. Now there is an additional term which localizes on the boundaries, and reducing over the boundaries gives the additional puncture anomalies. So in summary, the topological structure of the 4D anomalies follows directly from inflow arguments. Thank you.
The next speaker is Monica Pate.
Okay, I'd like to begin by thanking the organizers for putting together this conference. Today, I will be talking about color memory, which is a memory effect that arises in classical Yang-Mills theory. And I will also briefly discuss its potential for measurement and experiment. And what I will say is based on 2 papers I wrote with my collaborators Anar Clariu, Andy Strominger, Adam Ball, and Raju Vinagop. Now, the original memory effect, proposed by Zeldovich and Polnarev in 1974, was a prediction of general relativity, wherein the passage of gravitational waves induces a permanent displacement in the relative positions of nearby inertial observers. More recently, there has been a renewal of theoretical interest in memory effects due to the discovery of the so-called infrared triangle, which represents a set of precise mathematical statements that relate memory effects to soft theorems and asymptotic symmetries in generic theories of gauge and gravity. In particular, it predicts an analog of the gravitational memory effect for classical Yang-Mills theory, which will be the subject of my talk today. Now, by direct analogy with the gravitational memory effect, we readily deduce that its analog, the color memory effect, in words, is a permanent relative color rotation of a pair of test quarks induced by the transitive color flux across null infinity. Now, to unpack these words, consider the following thought experiment. Suppose we have a pair of test quarks at fixed separated angle on the celestial sphere at null infinity, and suppose at some initial retarded time, ui, they're in a color singlet. Now, in order for color singlet to have meaning, we actually also need to specify a flat connection on the celestial sphere. And for simplicity, let us take it to be exactly vanishing at the initial retarded time. Now, consider the effect of a finite duration pulse of color radiation flux that passes through null infinity after ui and before some later retarded time uf. Over this time interval, we take the quarks to be pinned to their respective angles on the celestial sphere, but of course evolve forward in retarded time. Now, by working in temporal gauge, in which the U component of the gauge field vanishes, we find that their colors do not evolve over this time interval as they traverse the source. At late times, all the radiation is passed, meaning that the gluon field strengths vanish and the connection on the celestial sphere is again flat. However, the classical constraint implies that while it is flat, it is generically non-vanishing. In particular, the classical constraint, which may be derived in an asymptotic expansion of the Yang-Mills equation about null infinity, relates the change in the flat connection to the flux of color. This is the origin behind the name memory effect, in the sense that the connection remembers the color flux even after it's already passed. And finally, the relative colors of the quarks are sensitive to this change in flat connection. Namely, at this late time, if you parallel transport quark 2 to quark 1 to compare their colors, you find they are no longer in a color singlet, but rather are related by relative color rotation, which is determined by the final non-vanishing flat connection. And finally, I'd like to mention how this classical color memory effect may be amenable to experimental investigation in deeply inelastic scattering events of electrons off heavy ions in the Regge limit. And so the basic idea is that the electron probes the heavy ion by exchanging a virtual photon. This photon splits into a singlet quark-antiquark pair, or quark dipole, which plays the role of the test quarks, and traverses the heavy ion, which is highly Lorentz contracted and plays the role of the color source. Now, there is substantial literature arguing that in the Regge limit, the dynamics can be described by classical Yang-Mills theory sourced by the hard partons in the ion. This means that as the dipole traverses the heavy ion, it acquires net color according to the color memory effect. Then, since the dipole cross-section is determined by the survival probability for the dipole to remain in a color singlet, it is determined by the color memory effect. And finally, the inclusive virtual photon heavy ion cross-section factorizes into a piece corresponding to the virtual splitting of the virtual photon into the quark-antiquark pair and the dipole cross-section, so it can be simply related to the color memory effect. So to summarize, I have described the color memory effect, which is the analog of the gravitational memory effect for classical Yang-Mills theory, and I have discussed its potential for measurement and experiment. Thank you.
The next speaker is Under Retolaza.
Okay, so let me start by thanking the organizers for putting together this very nice conference and of course for letting me talk about my work. So as you see, well, as Kungrun did, I will also talk about the possibility of having the sitter in a string theory, and in particular I will focus on the possibility of having the sitter by the use of anti-D3 branes on warp throat. So the talk is based on this article here, together with Jakob Moritz and Alexander Westphal. So, well, is it possible to have the sitter in a string theory? Well, one of the things that you can do in order to try to answer this question is to start studying what happens when you compactify and, well, see what the outcome is. So in particular, I'm going to focus on GKP type of compactifications And what happens is that there's some tension between two different perspectives when you do this. So on the one hand, you have the four-dimensional effective field theory description of a vacuum construction that, is supposed to give you the Sitter vacua. So in particular, in the KKLT construction, what one does usually is to start by first stabilizing your moduli by using fluxes and non-perturbative effects. And this way you obtain an ADS vacuum in 4 dimensions. And afterwards, one would add an ingredient, a localized object that breaks supersymmetry, such that you can uplift your vacuum energy in a controlled way. So the typical ingredient that does this is an anti-D3 brane on a word throat. So by doing this, you can see in this plot here that, for example, if initially you have this blue curve, you have an ADS vacuum that, by tuning your parameters, you can lift the vacuum energy, if you want, even to positive values, like in the green curve. Okay, so this is a bit in tension, as I told you, with the results by Maldacena and Núñez. So if you consider higher dimensional general relativity and you make a word compactification and such, it's possible to take Einstein's equations and from there write the 4-dimensional Ricci scalar that takes this form. It's basically an integral over the internal space of some combination of the energy momentum tensor coming from the different ingredients in our compactification. So from here we see that if you want to have the Sitter, at least you need some positive contribution to this integral, and therefore you need at least one ingredient that fulfills this inequality here. Such objects exist in string theory, but they're rather troublesome for GKP backgrounds, and in particular, anti-D3 branes make a negative contribution to this integral. So, there's some tension here, and this is why we decided to see what happens with this KKLT construction from the 10-dimensional perspective. So, what we did was to start with a two-derivative type 2B supergravity, and we took a generalized GKP ansatz, basically allowing for curvature in 4 dimensions. So, following the Maldacena-Núñez procedure, together with tadpole cancellation conditions, we obtain this expression here. So the 4D Ricci gets two negative semi-indefinite contributions, and there's one contribution coming from localized sources that could be either positive or negative. So once we have this formula, we can play the KKLT game and start stabilizing our moduli first. So we stabilize our moduli using fluxes, and we will consider a compactification where we only have one Keller modulus that we will establish with one Gagino condensate. So now we can use this formula to study what the gravitational reaction is going to be on the 4-dimensional Ricci of this effect. And in particular, the Gagino condensate, we all know it's a 4-dimensional effect, but in this paper here, they provided a prescription to describe this effect in 10 dimensions. So by using this prescription, we can see that after stabilizing all the moduli, the vacuum energy in 4 dimensions, or the 4D Ricci, is given by this formula here, where we see that it's negative, so ADS, as we had in 4 dimensions, and proportional to the Gagino condensate. So things match pretty well up to this point. Now we can see what happens when we put the anti-D3 brane on the word throat, because we want control over the compactification, and because of the dimensionality of the 3 brane, we would expect that it scales as e to the 4a. Instead, in this formula, we find this suppression, e to the 8a, so the new contribution from adding this new ingredient happens to be way more suppressed than what we should obtain naively. So what this is telling us is that even when you put the anti-D3 brane, the new contribution is negligible, and the leading order contribution to the vacuum energy is still given by this formula here, where the internal space has readjusted such that somehow you're obtaining an increase on the vacuum energy that scales like this. Therefore, this is telling us that, in the control regime, an anti-D3 brane happens to fail to uplift to the Sitter. Thank you.
The next speaker is Bogdan Stoica.
I would like to thank the organizers for the opportunity to speak here. And I would like to talk about certain decomposition of holographic entanglement that will hopefully appear in the next few days. So the motivation for this talk is that recent developments at the intersection of gravity, information theory, and field theory essentially suggest that in order to understand quantum gravity, we should really be understanding entanglement. And in particular, it's interesting to think about maybe broadly how geometry can arise from information, if it does, and also if there are some mathematical results that can be obtained as we go along the way. Now, everyone knows that in holography, the entanglement entropy of some region A on the boundary is given by the minimal area in the bulk, so that's the Ryuta-Kainagi formula. So this has been around for a while now. However, recently there was a different prescription introduced in the form of bit threads, which aims to make the Ryuta-Kainagi formula more local. And the idea is to imagine threads of entanglement that pass through the bulk between any 2 points on the boundary. And these are the bit threads, and we can, naively speaking, model them as divergenceless bulk vector flows which have bounded norm. The norm is bounded by 1/4 Newton. And then the entanglement entropy between a region A and its complement is literally the maximum number of threads that can be squeezed through the bulk between A and A complement. And the bottleneck constraining this maximum number of flows is just the minimal area by the max flow mean cut theorem. So here's a picture just to have a concrete image of what we're talking about. So for 3 regions, some configuration of bit threads. And the key insight is that the properties of bit threads should imply the properties of holographic entanglement entropy. So for simple properties of entanglement entropy, that is obvious, but for more complicated properties, it turns out that mathematical theorems are required. And this is one result that we proved on Riemannian manifolds. So it turns out that in order to show directly from flows certain holographic entropy inequalities, one needs existence theorems for threads on manifolds. And then this is one such theorem. So for n regions, one can put order n squared pairwise flows at the same time on the manifold so that the flows for each region AI realize its entanglement entropy in this way. And then it's not obvious, but it's a few lines proof from here to show that the monogamy of holographic mutual information holds. But one can actually go a bit further and ask whether entanglement should decompose in some way. And it turns out that for 3 boundary regions, the entanglement, and here I mean precisely this pairwise flows, can be decomposed into the entanglement of 3 bell pairs. And for 4 regions, we can't quite show it yet, but it's reasonable to conjecture that the entanglement should be decomposed into 6 bell pairs plus a remainder for region perfect tensor entanglement. And this gives a nice motivation for the monogamy of mutual information. The 6 bell pairs contribute 0, and the 4 region perfect tensor contributes positively. And going further, it turns out that this decomposition of entanglement translated into graph theory language implies a conjecture on the decomposition of an arbitrary graph with weighted edges into 6 graphs which encode the mutual information plus a remainder 7th graph which encodes the tripartite information. And in this example, 2 of the mutual informations are 0. And there is a further conjecture that can be made about state decomposition, and I guess you can ask me about that over at the poster session. Thank you.
The next speaker is Tomonori Ugajin.
Okay, so first of all, let me thank the organizers for giving me the opportunity to talk. Today, I'd like to talk about my recent work on the relation between scrambling and relative entropy. So the scrambling refers to the phenomena of quick delocalization of quantum states in thermal state, quantum information in thermal states. And typical time scale of this phenomena happen is so-called scrambling time, which is given by the logarithm of the number of degrees of freedom. And this implies that in a chaotic system, for any local subregion A, the reduced density matrix of thermal ensemble and its perturbation cannot be distinguished after the scrambling time. And this means that, okay, so if I could measure the distance between the reduced density matrix of thermal ensemble and its perturbation, then we can diagnose the scrambling. And in particular, the decay rate of the distance characterize the chaotic nature of the system. And in quantum theory, the distance, natural distance between two density matrices is given by so-called relative entropy. And motivated by this observation, we studied the dynamics of scrambling using the relative entropy in 2D CFT in large central charge limit, as well as several spin chain models. And this is a definition of the relative entropy. The relative entropy between two density matrices, rho and sigma, is given by this. And basically, this quantity measures the distance between these two matrices. And this is positive definite quantity. And it can be zero only when these two matrices are identical. And the setup of the problem we want to consider is following. We first prepare two copies of CFT and define the sum-field double state on top of it. And then we perturb this sum-field double state by inserting a local operator on one side of the CFT. And we then evolve the system both forward in time. And so from these time-evolved states, we construct two reduced density matrices on some region A. And we would like to calculate the relative entropy between these two reduced density matrices as a function of time. So we first computed this relative entropy in the large central charge limit, where we can use the gravity description as well as the RT formula. And the result is schematically given by this. The relative entropy is proportional to the central charge. And there's an exponential damping factor in T. So at the initial time, the relative entropy is proportional to the central charge. So we can distinguish these two states a lot. And however, at the scrambling time, given by the log of the central charge, this relative entropy becomes of order 1 quantity. And this means that we cannot distinguish the original thermal ensemble and its perturbation. We cannot distinguish these two density matrices. And after this scrambling time, this large C approximation breaks down. Because this is just an order 1 quantity. And so the quantum corrections to the RT formula become important in order to further follow the time evolution. And so we study the same entropy, relative entropy, in some spin chain models. And it contains two parameters, G and H. And by tuning these two parameters, we can make it integrable or non-integrable. And these are results of the same relative entropy. In non-integrable case, that the relative entropy continues to decay, meaning that the relative entropy, the system is scrambled. However, in non-integrable case, we can see the oscillation behavior at the right time, meaning that there's no scrambling in the system. And so to conclude, we consider the time evolution of relative entropy and discuss the relation to the physics of scrambling. Thank you.
The next speaker is Koji Umemoto.
Okay,
First, I would like to thank the organizers for giving me opportunity to be here. I am Koji Umemoto, a PhD student at YITP Kyoto University. And I'll talk about the new relationship between information theory and the ADS-CFT correspondence. And this talk is based on the works collaborated with Tadashi Takayanagi and also Yan too. And one of the most distinguished features of quantum gravity is given by the celebrated Bekenstein-Hawking entropy. So it tells us that the black hole has an entropy proportional to area of its horizon. And it has much more generic forms in ADS-CFT. It is so-called holographic entanglement entropy formula, or Ryu-Takayanagi formula. It says that the entanglement entropy in the CFT side can be calculated as a minimal area of certain codimension surfaces. So this relationship motivates us to study a deep relationship between the entanglement and the emergence of spacetime. So, but we have to be careful that the entanglement entropy is not always entanglement. So if you have a reduced density matrices rho AB, which is a mixed state, then the entanglement entropy is not represent the entanglement nor correlations at all. So for example, if you took some generic quantum, generic two subsystems on the boundary CFT in such a way, then because you trace out the remaining parts, the quantum state on these systems are mixed states. So you cannot use entanglement entropy to measure quantum entanglement in these setups. So our motivation is to find much more generic forms that connect the entanglement and geometry for such mixed state setups. So to do this, we consider the generalization of Ryu-Takayanagi formula by employing so-called entanglement or purifications in the information theory and proposing its holographic duals denoted by this red dashed line. The entanglement or purification is defined in this way. And you can intuitively regard it as a minimal entanglement in purified systems of given density matrices. And it captures it captures both quantum entanglement and classical correlations. So it is called the total correlation measure in information theory. And the holographic counterpart is called entanglement wedge cross sections. We defined it as a minimal area of corresponding entanglement wedge in ADS side. And we argue that these two quantities coincide at the leading order of Lagrangian limit. We have several supporting facts for this conjecture. First, we can show that the entanglement wedge cross section indeed satisfies all properties that has entanglement of purifications, such as entropic inequality by mutual informations. And also, we have a heuristic understanding why such dualities happens based on the tensor network descriptions of ADS-CFT. And also, we further show that the typical behavior, some kind of the phase transition of the entanglement wedge cross section can be reproduced by that of the entanglement purification in some toy models such as free field theories. And the last month, we further generalized this conjecture into the multi-partite setups. So you now have, for example, if you took a 3-partite case, then you have a rho ABC. Then we defined a new information theoretic quantity called multi-partite entanglement purification and proved its various information theoretic properties in generic quantum systems. And then we proposed its holographic duals based on the tensor network descriptions and shows that all properties we proved indeed satisfy this geometrical object. So these facts will support further the holographic entanglement or purification conjecture, and also it provides us new tools to investigate multi-partite entanglement or multi-partite correlation in ADS-CFT. So there are much things remaining to discuss, but so if you are interested in, please come to my poster. Thank you very much.
The last speaker of the Gong Show is Fei Yan.
All right. I would would like to thank the organizers for organizing such a wonderful conference and for letting me to speak here. Today I'm going to talk about line defect Schur index, Wallinder algebras, and U1R fixed points. And this is based on joint work with Andy Neitzke. So if I have 20 seconds, this is one of the slides I would like to show. So in this talk, I will introduce to you an interesting feature of the so-called line defect Schur index in 4D=2 series, first introduced by Dimofte, Gayoto, Gukov, and further investigated by Cordova, Gayoto, Shao. What we found is a close relation between the Schur index in presence of supersymmetric line defect and the value of the line defect on UR invariant vacuum of the serial compact pattern circle. And this relation is best summarized in terms of a commutative diagram involving three commutative algebras. In the following, I will introduce all the players of the game. So first, let's recall, given a 4D equals 2 SFT, one could associate a 2D Carré algebra a la Beam et al. And in particular, the Schur index is given by the vacuum module, a vacuum character of the Carré algebra. And one sensible question you could ask is, how do you get access to the characters of non-vacuum modules? And turns out one way to do it, which is not the best way, as many experts here would argue, but one way to do it is to consider supersymmetric half-line defects in your theory. Such supersymmetric half-line defects, they extend along a ring in R4 and ends at a point. And the endpoint support local operators, which you could count via the so-called line defect Schur index. And it turns out that, as first realized by Cordova, Gayoto, Shao, that in many examples, the line defect Schur index admits an expansion in terms of characters of a finite collection of modules of the Carré algebra, which are moreover closed under the modular S transformation. Given that, we could use Wallinder's formula to define a commutative associative algebra, Wallinder algebra, with the appropriate Furin rules. And moreover, this character expansion also sources you a map from the line defect OPE algebra to the Wallinder algebra. And it's a quite nice map in the sense that this is a home between two commutative algebras. And it's a very forgettable home, namely it collapses the infinite dimensional line defect OPE algebra to the finite dimensional Wallinder algebra. Now to introduce the third player of the game, we compactify your theory circle. And if you start with a 4D class S series, the 3D Coulomb branch is hitching modular space, and moreover, the U1R symmetry becomes a hitching action. Now, an important tool to use to study the geometry and topology of hitching modular space is the fixed locus of hitching action. And turns out that if your 4D series, the so-called Ajus-Douglas series, then the fixed locus of the U1R action actually consists of finite and many isolated points, which are moreover in one-to-one correspondence with certain height-weight modules of Carré algebra. And those are exactly the modules that appeared in the character expansion of line defect Schur index. Those are based on recent work by Andy and Laura, and further Du, Wenbing, and Kevin. So then you see there could be a potential relation of the fixed points, even fixed points with the line defects of P algebra and the Wallinder algebra. Now how exactly are they related? Let's denote OF as the algebra of functions over the U1 fixed points F. As a well-known fact, the modular S operation diagonalizes Wallinder algebra. And using this fact, and given the one-to-one correspondence between the U1 fixed points and the height modules of Carré algebra A, we could construct a canonical isomorphism, which we call H, from the Wallinder algebra to the algebra of functions over the fixed points. Now, the only thing missing is how does this relate to the line defect OPE algebra? So namely, you take the line defects wrapped on a circle and consider the WAV, and restricting the WAV over the U1 fixed points gives you the desired map, which we call G. G is also a very forgetful home. So those are all the players in the game, and we could organize this into a diagram. A natural question to ask is whether it commutes. As we checked in many examples, it commutes physically, at least heuristically. This implies that there seems to be a localization computation for the line defect Schur index using the UR symmetry. And if your theory has a flavor symmetry, we get a family of deformed commutative diagrams parameterized by the flavor fugacity. If you want to know more details about this, please come talk to me during the conference. Thank you for your attention.
I would like to salute the high quality of all the Gong Show talks, and I would like to ask you to thank all the Gong Show speakers again. And now this is the poster session, and I'm told it will take place in the area where the bento boxes were distributed during lunch.